Good morning.
Good morning, everyone. I hope I'm audible. And
Yes, okay.
yes, according to my watch, it's 9:30. I think we can start, Ilya.
Okay. Let me share my screen.
And I'll monitor Slack for you like yesterday.
Okay, good. Thank you. Where we are? No. Okay. Now share, and where are you? Here. Okay. Oops. Good morning, everyone. I hope we are all ready for the day 2 of our quick run for the basics of machine learning. And just a couple of comments about yesterday. I updated the file with the classifications. So I took out the regression and added two other examples of the classifications, application of the classification to the wine data set. So you can check it by yourself later. Okay, so so let me just quickly remind you what we have done yesterday. So yesterday we've done with you a very basic introduction kind of to the standard concept of machine learning. So when we were playing a little bit with them, the most basic family of the models, which are called linear regressions, and using this model as the model family, we define with you a little bit of kind of how you can make it more powerful with this idea of the feature spaces and or kind of the feature transformation, so that when we were able to with you successfully to fit the quadratic function using the linear regression. Yeah, but I mean, like this is overall, it's a very generic approach which allows you to play these games kind of on the quite a high level with very simple and explainable, which is very important machine learning model, because if you know that, I don't know, some features fit your data perfectly and make it what is called linearly separable. So that's what means that, if your linear regression works very well, that means that you can not only have a nice prediction outside of your model, but you can also try to build a theory kind of explanatory theory explaining why certain things are causing certain effects, which is much more important if you want to use machine learning for the real world application, whether it's in science or whether it's in, I don't know, in some societally related activities. Okay, so and we defined with you a very important concepts of overfitting and underfitting and or bias variance trade-off and how to try to play this game and how to navigate these two extremes. And the basic tool of navigation of these extremes is, of course, regularizations, and you can have various regularizations. And we also discussed with you how to train the models overall. And the training is, in some exotic cases as a linear model, or in some very simple cases as a linear model, you could have some quasi-analytical formulas, which will still requires from you a little bit of quite heavy numerics, which is not always well defined in order to navigate it, but much more often, or not much more often, essentially, in all practical cases, always people go for the numerical optimization procedures and the stochastic or gradient descent, just a gradient descent without stochastic. Stochastic is extra done. So just a gradient descent algorithm is a very basic algorithm for doing that job. Okay, so and we also look with you how we can transfer the ideas of the linear regression from a slightly different angle, which is a very interesting angle, which is the angle from the point of the probability theory or kind of the scene machine learning, or what is the machine learning model. It's essentially a probability sampler, which essentially create for you the data for some inputs, which is coherent with your training data. And that is why, if you have good enough probability distribution, the outcome of your training, so you have a good enough model which can model for your data. And why that was important for us, because that allows us to extend the family of our models to the classifiers to define the loss function for the classifier functions or for the classifier problems. And we also play a little bit with that. And afterwards we went with you and done some experimental games in Python and with scikit-learn. So today we're going to continue along the same way. I'm also going to introduce to you several families of the models, as you see already. So we're going to talk about the nearest neighbor algorithm and the decision tree, because this is slightly different family of model, which is called non-parametric model, but it's still a quite interesting and very sometimes overlooked family of the algorithms, which sometimes, if you don't have enough data, it's very productive or kind of useful thing to use things like decision trees or collections of decision trees or ensembles of decision trees, which are called random forests. Okay, and we're also going to touch few other algorithms which are related to the dimensionality reduction or kind of some problems in unsupervised learning. And we're going to finish with the very, very brief ideas. What are the neural networks? And ideally, there will be notebooks. I might not have a time, but I hope that I'll have a time to run briefly through all of them. But we're going to play around with the so-called clustering algorithms, unsupervised learning for the dimensionality reduction, and also some very basic neural networks. Okay. So let's talk about nearest neighbors and decision trees. And this is, as I mentioned already, is a slightly different type of learning, which is not really parametric type of learning in the sense like we're not going to have like, a bunch of bits here as we have in a linear model, or if we have it in a logistic regression. So when we take a linear model under the sigmoid function and so on and so forth. So, and it's also very interesting how you can build an algorithms even without these extra fitting parameters, but you still have a training. And now we're going to try to understand kind of training, what that kind of training procedure and how the algorithms works. And you can also think when such algorithms might be useful. Okay, so let's consider the following problem of the binary classification. Yeah, so we have the data set of the heights, and we have a data set of the kind of heights, weights, and we know that whether the person is required a large or medium t-shirts. So kind of like true means large t-shirt, false means medium t-shirt. Yes. Okay, so we have inputs, two-dimensional features, yes, height and weight, and we have a answer yes or no, or large or medium. Okay. And now, and we can, because it's a two-dimensional data, we can also plot it, into these sort of, there is our heights, there is our weights. So, and red means false, blue means true. Yeah, so kind of the blue means large t-shirt, red means red means medium t-shirts. And now we get a new point, this little star. And now the question is, how can we classify it? Where it's going to lie? Is this what would be the most likely label of this little new star? Can anybody guess? Okay, let's not spend too much time on guessing, and let's discuss the algorithm which is called nearest neighbors. And now the idea of the algorithm is that we are now going to try to see what is the closest neighbors and how many closest neighbors in this certain neighborhood are to this star. So and afterwards we're just going to take a majority vote. So who is the closest 3 neighbors, who is the closest 5 neighbors, and so on. Oops. So to predict a label y of the new point, we need to find k nearest neighbors according to some distance metric, and that's another thing which we need to think about, and assign the majority label. So if the most neighbors are medium-sized t-shirts, we're going to assign medium. If the most neighbors are large-sized t-shirts, we're going to assign a label large. Yeah. Okay. So, but now we can see obvious problem. So that if we say 3 nearest neighbors, it's obviously large. Yeah, we can draw a circle. And if we say 5, we are going to say medium. Yeah. And that's create immediate problems so that the outcome of classification of the algorithm is strongly dependent on the type of the extra parameter which we get. So in fact, although I call it non-parametric, in fact we have a parameter, yeah? And this is a parameter how many neighbors we're going to take into account. Okay, but there is also one more parameter which is not that obvious, is how we're going to measure distance. And there is various ways of measuring the distance. And most of you are well aware of Euclidean distance or standard Pythagorean distance. Yes, some of the differences of the squares of corresponding component and square root. There is also what is called L1 distance, which looks like this. It's just some of the absolute values. And there is very often, this is the standard 3 typical distances, 1, 2, and infinity. Yes, an infinity distance is just the maximum of the difference out of the all possible couples. Okay, but in principle, if you're talking about the distance, you can define the distance in any convenient for your space way. And in some sense, a lot of classification problems in many other algorithms or in many other instances is something like this, but it's just hidden, because you can see a lot of machine learning as that feature embedding. So what is a neural network? It's embed your data into some feature space in very, very highly dimensional. And afterwards, what do you see? You see a closeness of the certain points to the certain points. And you, in some sense, you are running something like this, but you don't even know about that. For example, when you do the classification with neural networks, or you do classification with some other algorithms. Okay, so, but this notion of the distance could be essentially anything, because distance is just a function. It's a function which satisfies certain axioms, and it's standardly it's supposed to be symmetric with respect to the exchange of the indices. It's supposed to be, at least in kind of like in normal spaces, not in Minkowski-like spaces, it's supposed to be non-negative, and it's supposed to satisfy triangle inequality. And any function of the 2 input vectors which satisfy those functions is defining some sort of a distance, including very, very odd distances, which one could not assume that it could be a distance. Okay. So, and based on the different number of distances, what one can and different number of neighbors, what one can get, we can go construct in that space so-called decision boundary. Yeah. So, and what we can see that as a function of the different distances, we have a slightly different decision boundary. So distance is our choice. Yeah. And as I mentioned to you, that also how to deal with some other odd distances. And the odd distances which would come around is, for example, the very famous is the Hamming distance. And this distance play a very important role, for example, in many places, but one of the places where this distance play a very important role in data analysis of genetic data, because that's exactly when you need to calculate the distance between two genes. That is the very basic way of how we can do it. And the Hamming distance is just how many different characters are between the two strings. Okay, so you have also edit distance, you have some other distances for the sets and so on. But what I mentioned to you, like you can define a distance quite straightforwardly, because it just it's a function which satisfies a set of axioms, and that's all. Okay. So also feature scaling, we also need to be careful about the feature scaling in this kind of approaches. Yeah. So that if you have a features which are on the very different time scales, instead of neighbors, we can get everybody more or less along the one line. But if we do the feature normalization and feature scaling, we can get a little bit more distinguished system. So kind of like that's another concern which one need to take into account. Okay. And of course, the problem with the such approaches is, but this is a generic problem of a lot of machine learning approaches with a lot of many dimensional data, which is called curse of dimensionality, is that in fact, when you begin to, as you increase the number of dimensions, essentially the analysis becomes more and more difficult. And the very prototypical example is that if we take a d-dimensional sphere, yes, kind of like two-dimensional sphere is a circle, three-dimensional sphere is a normal sphere, but you can imagine, or you can try to imagine that you can build it up more and more. And now kind of like if one is going to do a very simple exercise and try to calculate what lies beyond L2 distance of 0,09 of the radius from the center in 3 dimensions, it's almost nothing. Yeah, it's 3%. In 100 dimensions, it's already 63%. More than half of the stuff lies outside, just that very, very slightly reduced sphere. And in 1,000 dimensions, so it means that if your feature vector have 1,000 entries, it means that your input vector of the parameters have 1,000 parameters. It means that you are dealing with a 1,000-dimensional space. And in that case, if we do it for the calculation of the sphere, if we're just talking about the L2 distance, that means that the 99% will lie just outside of such a slightly decreased volume. So one needs to kind of treat it very careful. And that is why, kind of like, as you increase the number of dimensions, one need to carefully play with a KNN algorithm. But this is one of the algorithms which one can always try and see how it works. And in the practical part, we're going to do implement nearest neighbors algorithm, and there are some, again, rules of thumb how you can judge how many neighbors you need to consider, and also one can play the same game and try to consider what kind of distances one need to take into account. Okay. And now there is also a question. So kind of like parameters is everything which is required to produce the output. Yeah. So, and essentially for KNN classifier, we need the full training data set to produce anything. So it's called non-parametric, but from the point of view, there is no gradient descent and things like that involved. But one should be also careful that, all the time when you do something with KNN classifier, you need to use the whole data set. And in fact, when you use for the training, I don't know, neural networks or linear classifier with some gradient descent-like training methods, you can use only the parts of the data set, for example, in stochastic gradient descent and things like that. So there's always a trade-off. Okay. So, but however, yes, there is a case for the non-parametric learning. Yes, it's using the full data set as a parameters, requires careful treatment of feature scaling, but the main reason, the main decision, the value of k, and I will show you how we can determine which value of k is work good, but also we can play the same game for the distance function. Yes, and you see it's a quick and easy way to do some very basic analysis, and one can always use it and see whether you can learn something or not. And if you cannot learn something with the k nearest neighbors, you can just go to the next algorithm and try. Okay, so now let's go to another non-parametric algorithm, which is much more useful and rather efficient, which is called decision trees. And decision trees we use always, we just sometimes don't know about that in fact what we're doing is decision trees. And the typical example of decision tree, for example, here is decision tree in medicine. So if a patient or like a child have a fever and it's smaller than 2 days, it's this decision. If greater than 2 days and the child age is greater than 2, so we need to have as a function of the child days of fever and the child age, we need to take a decision. And based on this simple scheme, the medical professional could do some prescription. And in this case, yes, one can take a decision. And the question is, can we play the same game in the kind of like, but in this case, where this decision tree is coming from? This decision tree is coming from experience and kind of medical science, and somebody have built this decision tree and distributed to the medical professional. And in fact, what we wanted to do with this decision trees algorithms, we want to do something like that, but we want to have some way how this could be done on the machine level. Okay. Yeah, so kind of in order to simplify it, yes, so one need to kind of like do it not like this, not the days of the fever and how many days, but you can do it a little bit more formal and so that the decisions are taken on the Boolean variables, true or false, but in that case the conditions you embed into the nodes of the tree. Yeah, so days of fever greater or equal to 2, true, false, child age greater than 3, true, false, but this just make it a little bit easier for the machine to navigate the space. Okay, so and the decision trees, if we have some sort of training or construction procedure, it's grow from the top down. So we have main leaf, and afterwards we take some query based on our features, and if it's true or false, and that will be a question on which parameter we can take a query. So what are we going to decide we're going to look at? How we decided, if we're given this data set of the kids with these two parameters, days of the fever and several days of the fever and the child age, and the outcome, how we can build the tree. So we need to decide that first we need to do the decision based on the days of the fever, and on the afterwards assess the child age. So why not in reverse? Why not first child age and afterwards days of the fever? And that will be one of the questions which we are going to I'm going to kind of give you a basic idea about. So and we take one decision, and true false we build a kind of extra 2 leaves, and we have another decision, another question based on the features, and we build it until we can produce good enough classification or good enough regression solution. Okay, so how it could be written out formally? Yeah, so we get of course some kind of labeled data sets. Yeah, again, it's a supervised learning problem. Yeah, so we have an input axis, which are vectors, with a bunch of features, like in this case, days of the fever, child age, yeah, and so on and so forth. So D features, N inputs. And now if we have some random feature is equal to new is a subset of the entries which have some value new, and what we're going to do, we're going to kind of like in the training tree, we're going to create such loops for each subset. So if the data have the same label, return new leaf, pick the best feature. And now we're going to discuss what does it mean to pick the best feature, and afterwards new node of the decision tree. And now we're making this iteration until there is some stopping condition. So now the question is how we choose the best feature. And the best feature, or kind of the idea how we can choose the best feature, essentially is the standard science principle, which you might heard about, at least in the standard physics course. This principle is discussed, or Occam's razor, which is essentially says that, you need to go for always the simplest explanation. So entities that not to be multiplied beyond necessity. So essentially, at every instance of our building an extra branches, we need to take the most explanatory power. So now the question is how we can do it. So, and let's consider the following example. So let's say that we have a subset of data, and it's a high blood pressure and also education. So did the people have a high blood pressure or not, or what is their education level? And what we want to predict, is the person diabetic or not? And if we want to build a tree, we can build it high blood pressure, yes or no on top, or education, or what is the level education. And the very fundamental idea is, okay, so we can try to kind of like which of these which split we should do first, related to whether the high blood pressure or not, or what is the level of education. And the answer is we need to pick the most informative split. Yeah. So which can better predict to us diabeticity. So, and what would be the better prediction? So if we have a high blood pressure, no, we suddenly cut a whole lot of patients. Yeah. Okay. So, and now for that, or kind of the possible diagnosis, can you please make the window a bit bigger? I'm not sure that I can, because I'm on the full screen. And you can just download also the slides. The slides are in the... Okay. Okay. So let's continue. So what we're trying to do, we're trying to essentially what our job would be for every feature, we need to find the most informative split. So the split which is going to give us the most information. And as you're going to see, there is one measure of information which, okay, there are several measures of information that they're boiling down to the functions which are related to the information theory, or statistical physics, which are related to certain types of entropies. And that's what we are going to discuss just now. But essentially, in order to discuss it, what we need to discuss is, like, if we have, for example, a binary classification, so we need to have some measure which can distinguish these cases when we have only kind of items of one kind, the same number of items of both kind, and something in between. Yeah. So, and we can call it impurity function, but again, people with a little bit of background in standard physics and the statistical mechanics, they immediately, who've got the standard course of thermodynamics and statistical mechanics, they immediately know that, oh, we're talking about something like an entropy. Yes, so minimal entropy, maximal entropy, and so on and so forth. So, and that would be very close. Okay. Yes. So, and the obvious candidate, and again, the entropy in statistical physics have an extra coefficient, but essentially when the Shannon was formulating the uh, classical information theory and the measures of the entropy in the information in the computer science context, he just took this kind of genius breakthrough of Boltzmann and bring it into the computer science. So if we have a y, is there any discrete variable? So it means that, y could be taken, I don't know, n values, one of the n values. It could be 1, it could be 2, it could be 3, it could be so on, it could be n. And each value, 1, 2, 3, 4, n, and so on, and n, could have some associated probability with that. So the entropy of this y is just defined probability to have the outcome, corresponding outcome I, on the log 2 of that probability. And you sum all the events from 1 to n. Okay? So strictly, entropy maps probability distribution to some sort of impurity score. Yeah, because if you're curious, you can just do a very simple exercise. You consider two variables, and I think it might be the slide, and you have probability P and probability 1 minus P, yes, because the probability should be conserved. And in that case, you can just plot the graph P log 2P plus 1 minus P log 2, 1 minus P as a function of P from 0 to 1. And you're going to see that it's going to be curve like this, just kind of an inverted bow type shape. And it's going to have a maximum on 1/2, which corresponds to the maximum impurity, and the probability 0 and 1 correspond to the maximal order. Okay, so yes, that's exactly is the shape for the binary classification. So minimum impurity is corresponding to when we have only one class and no other classes, mean that we have probability is 1 if we drag in a random ball, yeah. So log 2, log of 1 is 0, so we get 0, and if we have 1/2, we get 1. So the maximum, so that's why we have a minus sign. So kind of like the maximum value is corresponding to the maximum impurity, and the minimum value correspond to the maximum homogeneity in the class, or something like that. Okay, so now can we use this idea to construct our tree? So kind of like we need to choose features for our first split. So we have our high blood pressure, yes, no, and education. So, and but because we already have some information here, so now we need to do not just entropy, we need to do what is called information gain. So kind of like if we choose the split based on education, what will be the information gain? How much more information we're going to get? Or if we choose high blood pressure, how much more information we'll get? And decision which of these to choose will be exactly based on have we gained more information by doing this or not. So this is your Occam razor to kind of like, is the simplest explanation is giving us the most. And what is the simplest explanation? Okay. So, and essentially, so what we're going to do when we need to calculate, or, when the scikit-learn is calculating to your decision tree, or even when it's calculating the ensemble of decision trees, which are called random forests, it's automatically calculating exactly this quantity on every step, which is called information gain, which is just your original information, yes, your original entropy, minus entropy of each subdivisions summed up. So we're taking what is the entropy of this group minus what is the sums of the entropies of this group. So if we do this split, or what is the entropy of this group minus entropy of this group, this group, this group, this group, and this group. And I think now one is going just explicitly do the calculations here. So, and yes, kind of very often this quantity could be written like this. And now we're going to get an example of calculation, yeah, of this information gain. So we have 30 instances, 14 blue, 16 orange, and we have a split. Yes, 13 blue, 4 orange, and 1 blue, 12 orange. So now what is the original entropy here is minus 16 over 30 log 2 16 over 30, yeah? Because what is the probability to get blue thing here is obviously 14 over 30. What is the probability to get the orange thing over here is the 16 over 30, standard probability theory, okay? So now let's play this game here. Now can we solve computationally via information gain, okay? So now let's do it. So high blood pressure, education, yes, no, and corresponding representative. So we need now to compute the high blood pressure if we do, so we need to compute the information gain if we do the high blood pressure split, or we need to do information gain if we do the education split. So our entropy from the beginning is the same in both cases, yes, minus 4 over 12 log 4 over 12, minus 8 over 12 log 8 over 12, and there is some number associated to that. Now, high blood pressure, we have two groups, yeah, which have the following, which will be the following, yes, 6 over 12 multiplied by minus 2 over 6 log 2 over 6, minus 4 over 6 log 4 over 6, plus 6 over 12 on 0. Why? Because this 6/12 is this guy, yeah, and 0 is a probability. And now this subset have a 6 entries, so probability that we're going to this subset is 6/12. And now what we have here 2 blues out of 6 and the 4 oranges out of 6. And this is your 2/6, log 2/6, 4/6, log 4/6. So we're going to get some number, yes, which is 0, 4, 5, 9, whatever. Okay, now we need to spend a little bit more time in calculating all of contributions from the splits which are coming from the educational split. So 1/12 from 0, yes, because there is no options another. And where is not another 0, 1/12 from 0? Now we have 3, yeah, 3/12 on corresponding split, 1, 3, and 2, 3. Again, the same thing. Yeah, and here we have 4, but 3/4 and 1/4, and we get something like that. Okay. So, and now we can calculate what is the information gain, what is the original entropy minus entropy with respect to the split. And we get that this gives us the bigger information gain. So we learn, according to the measure which we suggested, more by doing the first high blood pressure split. But if, to be honest, in this particular case, that was more or less obvious, and I hope you agree with me. And that seems to be a little bit more relevant variable than education. Okay, so there is some answer, yes, but it's not to me, I assume. Okay. So, and it's clear that the first should be a high blood pressure split. And afterwards, the next split we need to do based on education, for example. Okay. So, but also what could happen, yes, what could happen when you build the tree is that you can also do overfitting. Yes, kind of, and there is this, and it's a standard thing. And what will be in the case of the trees overfitting means, in the case of overtreating means it's mean that you have too many branches, and essentially when you end up that in the end of your classification there is only one representative for each sub branch, it's mean that you're clearly overfitting because you're describing everything. Yes. So of course, this is a generic recipe, get more training data. Yes, you can try to remove irrelevant attributes. Yes, which is not always possible, but sometimes you can do. Yes, we need to stop growing the tree when there is no statistically significant information gain. So for example, in this case, we can say that, okay, if we do the split by the all remaining features is so small, the information gain is so small that we don't need to do that split because we haven't learned anything. Yeah, and yes, you can try to overfit, but afterwards throw away some branches, which is called post-pruning. Okay. Yeah, so you can try to play with the different hyperparameters, again, the tree depth, splitting criterion, termination criterion, and yes, and how to estimate the generalization performance using the cross-validation, which we've seen. And as you've seen, it's like built in naturally. So it's not that you need to do it from the scratch, it's built in. Yes, you can also add some extra things like regularization, but in this case, you are adding complexity using some performance measure and so on and so forth. Okay, yeah, you can stop growth. You can decide, that as based on the number of feature, you can say that, okay, what will be the maximum number of generations you are prepared to go this, and it's a max depth parameter in scikit-learn. Yeah, set a minimum number of samples per node. Yeah, so that again in scikit-learn it's have a parameter so that you don't try to classify one entry. Yeah, so minimum number of samples per leaf also is, and again use the k-fold cross-validation and so on. Okay, so there are some other ideas to avoid overfitting. And and these other ideas are exactly related to this idea of averaging or ensembling, and this is a very common idea in many machine learning algorithms to add some sort of randomization, or you can, in this case, you can create a multiple decision trees, and they all could be slightly different, or you can train them on the not on the whole data, but on the subsamples of data. And in fact, now it's there will be a later slides on something which is called ensemble learning, or kind of how to use many trained models together to give you a better result. And there is a strong mathematical result on that, which I'm going to mention. And also, you can use not all the input features, but the subset of the input features. And what you're going to see that this, in that case, if you do something like this and average out result, you can get a much better results. Yes. And for example, you can do if you do this one, so you train on the subsamples and not on all input vectors. I mean, not a full range of the input vectors. You can just randomly choose a bunch of features. So you get a whole slew of classifiers. Yeah, for example. And afterwards, what you do, you bring in new example, you get the answers from all of them, and you, for example, do just a simple majority voting. And that's in a nutshell a very simple description of how the simple ensemble works. Okay, yes, and that's bringing us to this idea of the simple ensembles in this particular world, which is called random forests. Yeah, so we have the training data, and what essentially is happening is it's spreaded randomly into the subsets. They are trained separately, and afterwards there is a voting procedure of the each classifier, which is trained on the subset of data, and also could be on the subset of features. Yes, on the subset of data and the subset of features, and afterwards they are reunified. And as you've seen yesterday, this random forest classifier just out of the box was working much better than the linear regression model. Okay. Yeah, so again, there is a standard procedure, but I assume that we can probably don't spend too much time on that, because that's just formalizing what I just said, and again, it's just implemented in the scikit-learn, and we just need to straightforwardly using it. And the benefits is, yes. So why you wanted to use it, and this is quite important. You want to use it first of all because it's very fast. It's much faster than training neural networks. It's also working, and it's working in a controllable way on the small data sets, because what you're going to see with the neural networks, or what you might heard about the neural networks, and what I've also shown yesterday in my lecture, that that even that very kind of simplistic and very primitive GPT-2, which was issued in 2019, it was already using 1.5 billion parameters. So in order to train this 1.5 billion parameters, you need a lot of data. Even on that instant, that was a lot of data. And of course, the modern machine learning architectures train on even larger corpus of data. So essentially, it requires a lot of data. But if you're in your real life research task, you need to perform, I don't know, classification or regression problem, and you have, I don't know, 100 points, 200, 300 points, or maybe 1,000 points, which is still very small, and one should be very careful applying neural networks for that. The random forests or decision trees and the ensembles of decision trees, which are called random forests, is extremely efficient way of getting a very good prediction. And as I mentioned to you, very importantly, that afterwards you can do the feature ranking, and you can understand what will be the most important features in your data set. What is the real reason why your classifier is, if it's working, it's working correctly. So because this feature and that feature is the most important one, and you can afterwards try to build some theory based on that, or try to understand what does the outcome of the algorithm means. Yeah, so, and there is some technical things. So because there is a scale invariance, which is very useful. Yes, because if you do the kind of this training on the subsets and on the subsets of the data and the subsets of features, it's much more resistance to overfitting, because you're not fitting the whole data set. You're always training on the small part and afterwards averaging out. Yes, and yes, it could be from the classifications, it could be turned into the regression. So we can do it for the continuous data. Okay, so but also because you're training a lot of trees, it could be easily parallelized, which are independent. Yeah, so it means that you can take hundreds or thousands of processors and train thousands or hundreds of trees, and afterwards averaged out in the end. So this is a very straightforward and very simple parallelization. Okay. So kind of like we need also to talk about, the richer model families, and also we need to talk about ensembles, because ensembles, as I mentioned to you, is a very natural way of pushing the uh, pushing the efficiency. And just outside of the as a simple example, a few days ago there was a defense at the Stellenbosch University of the student or PhD student to whom I have some a little bit of co-supervision, and in one of her machine learning tasks she was using these ensemble techniques, and not fancy neural networks, but the uh, some of the boosting approaches, because the data was not that large, and the neural networks wouldn't work in that case. Okay, so what is ensemble learning? And ensemble learning is based on the very simple mathematical idea, so that you have kind of like, and we've seen it yesterday, so that we can train a classifier or we can train a regressor, and it works, but not perfectly. And the question is, like, if I have a lot of models which works poorly, which just above 50%, which is called weak classifier. Yeah. And if I take them together, can I use them to create a more powerful model? And there is a strong mathematical results, which mean that there is a theorem which is proven, so that if I have large enough number of the weak classifiers, so that the classifiers which have just probability of binary classification just above 50%, it's not 50%, so it's not completely random, but it's less, just above 50%, I can make, as the function of if you give me enough of those, I can make it as arbitrary close to one as possible. Or I can make something which is called a strong classifier. Okay? Okay, so the examples of these approaches is used, for example, in the recommendation engines. Yeah. So, and in many other places. And it's very often not neural networks, not because of not because they give fast training, fast additional training when you have a lot of data, and it works well. Okay. Sorry. Okay, so there is a question about, sorry, Tutukili, are you around? Because you missed the question about in the, okay, I think it's a question about something like that. Ah, no, there is a reply. Sorry. Ah, yes, it's answered. Yes, I assume. Yes. So the first two terms are multiplied by zero, because the probability to find object here is here we have a one kind of the log of one, and log of one is zero. Like here we have, sorry, here we have three candidates, yeah, two of the one class and one of the other class. So if we draw a random candidate, the blue one will have 1/3 probability, we have 1/3 log of 1/3, and the orange candidate 2/3 log of 230. And somewhere I think it was, where it was this one. Yeah, so kind of like 1 log of 1, yes, and 0 log of 0. Yeah, if we calculate, assume, yes, that's, sorry, and what was the next thing? Is there a way to programmatically detect overfitting? Relying on R-squared value does not seem to help. Because training. Yes, there is a way to programmatically detect overfitting, and that was discussed yesterday. So you need to, I mean, for this kind of models, you need to understand what is the model capacity and how it's behave, and plot the graph of the test with training error as the function of the model capacity of the or model family capacity, and see at which capacity your test and training errors should go down, and on some stage the training error will still go down when it's kind of like because you're just starting overfit, but the test error will start to go up. So in that instance, when they begin to diverge, you need to stop and that's your sweet spot. But that was discussed yesterday. Okay, sorry, let me go back. Where we were. In ensembles, okay. So, and this is a typical problem. Yes, kind of predict the rate of the movie based on the user ratings and so on, and other ratings of other users. And Netflix were running it as an open competition. Yeah, and somebody won the main prize by using the ensemble of 800 plus rating systems. So kind of like it was 800 plus classifiers, and when the person makes a very specific, a special type of ensemble, that method works. So in principle, it's a very efficient method. And on some stage, I don't know what the status now, but on some stage, and not that long time ago, a lot of search engines were running on some sort of these kind of things. I mean, on ensembles or on trees and things like that, and not on the neural networks. Okay, so there are different strategies how you can construct the ensembles, or how you can do this kind of averaging of the results of the multiple classifiers. There is a strategy of random forests, and there is a strategy of what is called gradient boosting decision trees. Okay, so kind of like what is, and it's clear what strategies you could have. I mean, there is a simple strategy. If you have a regression, you can just calculate an average. So this is as simple as it gets, and it's the most simple idea, but even that could give you a very good performance, because you just have a lot of, and as I mentioned, kind of like there is a mathematical theorem which is saying that, this is a good tactics. Okay, yes, for the if we need to do regression, and if we need to do a classification, we just do a majority voting, for example, for the binary classification. Yeah. So what this means, so that each of those fi is spitting out to us 1 or 0, yeah, and there is a k of them, and if we sum of them, because it's a k of them, it could be greater than k over 2 or smaller than k over 2. Yes, and if it's greater than k over 2, we assign 1, so it means that the majority is thinking that it's a class 1, and if it's below k over 2, it means that the majority is thinking that it's a class 0, so the classification will be 0. Okay? Now you begin to get a little bit fancy. So you can not just average so-called Bayes model or weak classifiers or weak regressors. Now you can weigh them in. And what does it mean? Because now it means that we need to have an extra procedure of determining this coefficient, because this is obvious generalization of this, yeah? Where that betas are 1 over k and they're predefined. But now what you can do, you can now decide on the subset of data, what will be the best betas. So you use one subset of data to train all FIs, and you use another subset of data to fit this coefficients beta of the ensemble. Yeah, and more general, you can have any second layer, which is going to, it could be not, because this is like a linear regression. Yeah, it is a linear regression, and from that perspective, you could see these classifiers as the feature embedded. Kind of like, and in principle, we go back to the very beginning of the yesterday's lecture. Or you can, more generally, you can have some nonlinear function, which you are training on using not x's as input, but f of x as input, fi of x as input. Okay, yeah, now we're coming to the even fancier ways of combining the Bayes model. We could have, not only weak classifiers, but also we could train extra function of the input data, which you can call experts, which is just going to tell us essentially what they're going to tell us. In some sense, they're going to tell us, okay, so this guy or this classifier will be good on this kind of data, not on overall data, but on this kind of data. So it's and from this point of view, you get a little bit better. So kind of like that, you have a lot of weak classifiers, and subset of them is the good on, I don't know, on one distribution of the input data, and another bunch of the weak classifiers good on the other distribution on the input data, and these functions are going to alternate between those. Okay? So essentially, yes, what do we need in order to play the ensemble game? In order to have an ensemble, we need to have a good enough diversity. Yes, so we need to have a different model families, different training data, different features, different hyperparameters. So, and the intuition why ensemble works is really written here so that, when you train on the different subsets of the data and the different sets of features, each classifier is going to be wrong, or each regress is going to be wrong on the different subsets of data. And so when you average them in some fancy way or straightforward way together, the majority will be correct on the data because each classifier is lying on the different bits and pieces. So when I'm asking what's happening in this particular point of my input space, there will be more classifiers which are going to be correct exactly here than some than in some other places. That's why, kind of training on the different subsets of the features and the different subsets of data is so important because, you can really try to make really independent mistakes. Okay? Yeah, so it's essentially, yes, there is a little example, so that with the classifiers, with the different accuracies, and how you are going to put them together, that they're supposed to make mistakes on the different subsets of data. Okay? That was our supervised learning. So supervised learning means input with the labels, yeah? Question number 1, answer. Question number 2, answer, or input point, corresponding answer. Now we're going to speak a little bit about the unsupervised data. So let me see. There is nothing in the chat. Okay, so let me go to the unsupervised data. Okay, so the unsupervised learning is also extremely interesting and very useful thing, and you need to use unsupervised learning also as the additional feature to your supervised learning task. Even if you need to solve supervised learning problem, very often you use unsupervised learning to add extra features or extra dimensions to your supervised learning task, and suddenly your performance of your supervised learning could grow very strongly. Okay, and we were discussing with you yesterday. I told you that that what the unsupervised learning is doing, it's you given some data point without structure, you don't know anything, you just have a data points, and what the algorithms are doing, they allow you to find some hidden structures in the data, meaning that, for example, on these two-dimensional pictures, if our points are points like this, what the unsupervised learning algorithm is, we're going to tell you that these points have something in common, these points have something in common, and these points have something in common. And obviously, in this particular case, it looks like the commonality is proximity, yes? So these points are close to each other, this is a little cluster, and this is a little cluster. And you as a or the person who's using machine learning or machine learning engineering approach, what you need to do, you need to go back to your data after you get this answer and try to understand what's common between this point or what's common between this point and what is different between these two families. Okay, so types and uses of unsupervised learning, and as I mentioned to you, one of the very important usage of unsupervised learning is what is called dimensionality reduction. So because when your input feature have a d dimensions, so your input features are vector with a d entries, yeah. So if you apply unsupervised learning, you can identify what will be the most important combinations of the features, and you can essentially throw away the rest, which are not that important, and that corresponds to your input vector becomes smaller. And of course, this is a very useful approach because if you have a million input features, and what is a million input features? It's just an image 1000 by 1000 black and white image. Yeah, if you input black and white image 1000 by 1000, which is it's a relatively small resolution, it's a million input features. So it's not something outrageous. So there are some special cases, which is called clustering, which is, we can see here is a typical example of the clustering. Yeah. And, there is a feature learning for pre-processing, exactly what I mentioned to you. So by using this, we can also introduce new features and add them to our supervised classification. Yeah. Compression. Yeah, so what does it mean? For example, what is everybody knows what is the JPEG files, yes, and what is the JPEG files and why they're so popular? Because that's the difference from the standard your bitmap or TIFF file, which is essentially information. This point, this color, and this color means three numbers, yeah. This point, this color, and so on. It compresses that information very efficiently using some techniques which are built in, which essentially is some form of unsupervised learning. And yes, you're going to see that it also allows to do visualization quite nicely. Okay. So very simple clustering is a k-means clustering, which have very, very close ideologically with the nearest neighbors. Okay. So what is a clustering? So we have a bunch of points, and what we want to do, we want to discover a mapping that discover natural groups in the data. So, and the question is, what will be the good metric? What are we going to measure? What does it mean, the clusters? And we need to measure the clusters, we need to discover some sort of metric. And you can see, kind of like, if we have a data like this, of course, it's clear what does the clustering mean. But if we have a data like this, what does the clustering mean? Or if we have a data like this, what is a good clustering? Or if we have a data like that, what would be the good clusters in the data? And for us, it's obvious what should be the answer as the humans, and because of this two-dimensional representation of data. But imagine that you have this situation in many, many dimensions so that you cannot easily visualize it. Okay? And obviously, here's a little example which one can use. So if you have a green, red, and light red circles, yeah, which are clusters. And of course, this one is obviously should be the green one. This one should be the same color, these guys. This one should be obviously red, but the question is, who should be this guy? Should it be one of these or one of those? And now, what does it mean? Now we need to define a way how we're going to do it. And the typical and easiest way of doing it, various ways of doing it, is a k-means. So essentially, how does it happen? You calculate what is the center of this cluster. Using some distance measure, you can describe, kind of calculate what is the center of these positions, and it's called centroid. And you calculate it to everyone. And afterwards, what you need to calculate, where this point is closer to the which centroid. And obviously from here, what you can see that the closest, if we are talking about some sort of Euclidean distance, is obviously this one. Okay. But naively, we would think that it's one of the red ones. But the center of this cluster is somewhere here, so it's further away. Well, this one is somewhere here. Okay. Yeah, so in more real world situation, you are getting something like that. Okay, so how the clustering algorithm is looking like, you randomly assign the point, and afterwards you loop until converges until you find the corresponding centroids. Okay, so let's go to and we'll have a little what is called notebook file where it's implemented, but it's also part of the scikit-learn. Yeah, and afterwards, after we find the centroids, we can just calculate the average distances to the centroids and what is the minimal distance that will be our corresponding new assignment. Okay. Yeah, and the k-means is quite sensitive to initialization, but again, this is all the technical problems which are usually taken care by the software. So let's just go quickly to the more how the model define the center of each cluster and how the algorithm define the number of clusters. Okay. Yes, so that I quickly run over. Okay, let's go back. So first of all, who are the clusters are. So the cluster representatives. And afterwards, yes, you just follow the algorithm. So we randomly choose, okay, what you can do. I mean, if we don't know the cluster families, we can choose randomly, we pick, let's say that we think that we're going to have a k clusters, we randomly choose them. And afterwards, what we do, we calculate the distances from this to everyone else. And to the closest centroid and working in the cycle. But we're going to have an IPython notebook which is going to explain to us. Okay. So, and essentially afterwards, slowly you update the position of the centroid and you get it slowly. Okay, let's go to the dimensionality reduction. Okay, so with the dimensionality reduction, it's useful because it's reducing the complexity, and yes, it's kicking out what we have yesterday. We've seen a highly correlated features, which essentially is not necessary. Yes, and it allows to remove less informative features. And the very standard thing. Okay, so will be principal component analysis, which we're going to discuss just now, but let's go into the how we can formalize it. So we can formalize it in the following way. Yeah. So we have our input data. So we have n input points. This is our features. Yeah. So we can rewrite each input sample as bunch of D features. Yes. And they could be written in some basis, it's called. Yeah. So kind of like as the vector 1, 0, 0, 0, 0 and 0, 1, 0, 0, 0 D times. Yes. And what the job of the dimensionality reduction is that we can rewrite each feature approximately as a state in a new basis where this number of the basis vectors, which will be not necessarily 1, 0, whatever, but it will be something a little bit more involved. But there will be much smaller number of those. And the typical example of traditional or classical dimensionality reduction is what is called principal component analysis. And how does it look like? And it looks like very, very, very simple. So if we have, the bunch of points, yeah, and they're looking like this, we could really think quite strongly that the points mainly vary around this axis and a little bit vary around this axis. So to describe the most diversity between the points, we need to first walk along this axis, and afterwards we might take into account the moving along the orthogonal axis. Okay, so and what formally and mathematically what is happening? We get this axis will be exactly along this line. Yes, so that's what is increased or describe the majority of diversity in data. And the orthogonal axis which will be filling up the space, yeah, the remaining one. Okay. So, and there are various ways how you can construct this dimensionality reduction. And there is a question, can we do the sorry. Is it possible to do some coding example of the clustering? Okay. It's possible where we are now time-wise. Okay, yeah, we have plenty of time. Okay, let's go into the coding example of clustering. Okay, okay, okay. Okay, so what do I have here? I have here first PCA. Okay, so this one and this one. Okay, now let's go for this one and okay, sorry. Okay. No. We're here. Let me also, let me also make it, I think it should be, Okay, sorry. Let me stop for a second and make it visible. Okay, so notebook is in the canvas. Okay, so let me go back and we'll skip for now PCA part of the notebook and go to the clustering, blah, blah, blah. So, data. So what do we need? We might need something outside of here. Okay, okay. So clustering. Okay, so with the clustering, so we need to pick number of clusters, which we assume or we think is an optimal number, but you can decide what is optimal number. You just need to run it for the several clusters, and afterwards you see initialize k points as a centroid randomly within our area, attribute each observation to close the centroid, update the centroids, and repeat these steps until centroids are stable. Okay, so what do we first? We need to create the clusters here. Okay, I need here a numpy. Yes, so that's what and we need also matplotlib. Yes. SPOT or something like this. Okay. Oops. Sorry. Pyplot. Okay, that's better. Okay, so what are we doing? So first we say that because it's we need to create a data set, which is just 150 points in 2 dimensions. Yeah, and their X and Y are going to be randomly assigned from the normal distribution. Yeah, so numpy random normal, yeah, in the various locations. So we have something like this. Yeah. So now what do we need to do? So we have our data set. Now what we need to do, now we need just to do what our algorithm is describing to us. So we need to initialize case centroid randomly within each space of our data. So that's what we're going to do. And to calculate the distance, we're going to use a SciPy. Yeah, so we're taking the centroids and we're just creating them again from the 6 random points, and we just putting them in. And now we're going to calculate, to do this loop of adjusting the centroids. Okay? So what are we going to do? We're going to calculate the distances between the all points and the centroids. And afterwards, what we're going to do, we're going to calculate what is the average value of each of the centroid to the each of the labels. And let's see how the assignment is happening. So on the first step, it's a 4 random points. And now already after the second step, the centroids are moved and they're slowly moving to each corresponding cluster on each step. And that's how we identify the centroids. And if we converge, it means that we choose the right number of clusters. Okay? Are we good with that? And afterwards, what one needs to do, one needs to decide how many clusters do we need. And I think that should be also in the, so essentially how many clusters do we need? We are calculating based on the following quantity. This is called d of k or whatever. We're going to plot it. And essentially we're calculating what is the over our clusters. We're calculating the following distances, distance between the point and the centroid, and we are just checking it between the steps. On the previous step, on the current step. And okay, here we're just using the built-in k-means into the scikit-learn just to make it easier. And this is done for the various numbers of clusters and for our data set. And essentially, we could try to identify one cluster and we can calculate this quantity. 2 clusters, 3 clusters, 4, 5, 6, 7. And we see that it's drastically decreased till 3 and afterwards it shallowly decrease. So that exactly means that, we should stop at 3. Okay. So you can play with the code. Okay. Oops. Go back to the dimensionality reduction. Yep. So what is the principal component analysis? So we are changing the axis in our data and introducing some new effective axis, or you can say that it's a orthogonal projection of the data on the low dimensional linear space. But what does it mean? It means that you choose the such axis that you can kind of maximize the variance of data. So, and as I mentioned to you, kind of like just even without all the mathematics, if we look on all of these points, we can see that, the most diversity in the data or the most variance in the data will be described along this axis. So it means that we need to first project along this axis and afterwards project along this axis. And as the function of what is our precision we required, we can consider moving along this axis first, and only afterwards, if we need to describe the whole diversity in the data, we could consider the orthogonal component, but already going this way is describing well enough to us. Okay, so mathematically, it could be written like this, as I already mentioned, yeah. And so kind of like if we want to see kind of can we have from our data one-dimensional representation, so what we need to find the such a vector v, which is essentially maximizing the product or kind of the doing the best projection. So for given v, the projection is defined like this. So we just now need to only to find v. Yeah. So in order to find v, what do we need? We need to do the minimization problem. Yeah. So we need to make sure that this kind of like this vector v is explaining, if we want to project it on 1D, the maximum variance in the data. So we need to minimize these differences, and that's kind of optimization task essentially. So, and we need to solve this optimization task. And yesterday we've seen already with you how similar optimization task could be solved. Yeah, so how we can find these directions? For the zero-centered data, we can build the covariance matrices. And for any unit vector, the variance of xi with v1 is following this formula. So in order to maximize it, we can set this and to find the first eigenvalue or eigenvector of covariance matrix. Okay, so and for more than one dimension, so we can go for this standard procedure. So we can subtract means from the order dimensions of X, compute the covariance matrix, choose the first vector of VD as the first vector of the covariance matrix. Afterwards, subtract the effect of the first vector and do it again and repeat it until we have the representation as it makes us happy. Okay? And we are going to create our low dimensional representation of the data. Yeah, and again, this is a standard example, as I mentioned to you. So if we have a Gaussian data set, which is elongated like this, so the first vector v1 is, or kind of, it's called the first principal component. This is called second principal component, which is orthogonal to it, and you use it iteratively, if you have more data. So if you take into account this one and this one, you can explain all the variants in the data, but that's not, I mean, that wouldn't give you any dimensionality reduction. But if you go along only this component, you can explain a lot of variants in the data, but of course, you are making some kind of errors, but this also could be used. This component of the data or this feature transformation could be used as an input into your supervised learning scheme. Okay, so, and PCA algorithm is a standard bit of the scikit-learn, but if you want to implement it from the scratch, that's what you're going to do. So you're given data. We're computing the various metrics. X have these dimensions, so we need to compute the data mean over all averages, subtract mean from each row, so that we're centering the data, compute the covariance metrics like this. So the PCA basis vectors on new coordinate axis, or this v1, v2, and so on, will be given by the eigenvectors of the covariance matrix, which could be, of course, done standardly using NumPy, SciPy, and so on. So which is going to spit you out the list of eigenvectors and eigenvalues, yeah, which are going to be ordered, and this will be your first principal component value, and the corresponding Q1 will be principal axis. Yeah, and of course, it will be D values, but as I mentioned to you, kind of like in the multidimensional case, there will be some components which are long and some components which are shorter, and you just naturally need to introduce some cutoff. Yeah, so for example, there is a typical distribution of how much of the variance is explained with which component, and the first component explains a lot of variance. I mean, this is one of the examples in the data. This explains small and small, and you can say, okay, if you explain less than 5% of the variance of data, you're just ignoring it. And as a result, instead of 10 features, you get only 4 features in your data set. Yeah. Typical example of the PCA for the visualization is one can try to do it for visualizing some data, and we've seen it, for example, for the 2-dimensional data, this is our visualization, and if we project it on 1D, we're just going to get, a line with the different distribution of the points. You can try to do the visualization of the famous MNIST, which is a handwritten data set, but it doesn't look very impressive. Yeah, so if we take a lot of numbers, it's a classification problem, which with numbers 1, 1, 1, handwritten differently 2, 3, 4, and so on till 0, 10 digits. And if we want to apply PCA with the 2 components to use for visualization, we're not going to get a nice result, which means that, PCA do not work very nicely for this kind of problem, but it works very nicely for that other kind of problem. And that, PCA is often used as a preprocessing step for the supervised learning. It's reduced dimensionality, eliminates, so kind of, if you do this procedure, and where is our covariance matrix? So in this covariance matrix, if we have a strongly correlated features, they are going to be kicked out from our eigenvalues. Yes, because they contain the same information. So yeah, and this could be useful for visualization, but with PCA, sometimes it's work. What we're going to see, I think, in the same notebook which I shared with you about the k-means, over there we have an example when nonlinear form of embedding into the low dimensional space is called TSNE, is working much better for the digits data set. Okay, yes, and that's exactly the example of that. So beyond PCA, because PCA is formally speaking, it's a linear transformation. It's essentially what you are doing. You are taking your data set in the multi-dimension and you are rotating it in a very specific way. And you are rotating it and you are saying that in that new rotated basis, what is going to happen? You're going to have the axes which are most important and the axes which are least important. And that information you just throw away. But as you see, I mean, for example, with the digits dataset, it doesn't work that well. But there are some other nonlinear dimensionality reduction techniques. For example, there is this isomap, or which is more interesting, is a TSNE, which is straightforwardly implemented, I think, also within the scikit-learn. Or if not, there will be a package written which we need. But we're going to see it in the examples so that some nonlinear embedding or stochastic nonlinear embedding technique, it works very well and it allows you very nicely to embed even such a difficult for the linear separation problem as classification of the handwritten digits. Sorry. Okay. Yes. That's a good answer. So that, yeah, because I could not zoom closer on my screen because I'm in the full screen. And that's a local issue. And intuitively, what does covariance has tell us about the data if you couldn't make an example with the Gaussian you've previously shown? But I mean, covariance is exactly telling you that what the example with the Gaussian have shown you. It's telling you along the which axes, your data is changing more, or it's kind of have more variance or less variance. Okay. Okay, so do we have, okay, so we have 5 minutes to 11. So let's maybe do the PCA beyond third and fourth component information about the data set. Okay. So the PCA, what do you do usually with PCA? So it's because it's a rotation of the space. So the question is, do the PCA beyond third and fourth components contain information about the data set, and what I inherit to find first and second component that contains relatively more information compared to the third and fourth and fifth, etc. components, or each component contain unique information and that must be explored. Okay, so the last bit, must is the wrong word, but it's always a question of precision. And what you need to do, oops, sorry. Let me go back here because this is the most important plot from this perspective, or is in the notebook, it's in reverse. If you take the first component, how much of variance you explain. If you take as first and second, how much of variance you explain. So what you need to do, I mean, you are always, and there is no free lunch. This data set have a 10 features, but you can say that with your precision of the problem which you are solving, you don't need that much information and you are prepared to trade off the precision of your algorithm but onto simplicity of implementation. Because if you have a 10 input vectors, or kind of the input vectors with the 10 components, and you have an algorithm which you are writing with the input vector with the 4 components, it's much more simpler algorithm and you can make much more sense. And don't forget that, when you're taking the all information contains in a data set, it's a very dangerous assumption that there is all what contains in the data set is information, because the data set also naturally contain noise. Because if you think about if it's a data set from some, I don't know, physics or whatever, chemistry, biology measurements are inherently imprecise. So if I measure something 1.1 of whatever kilogram, it doesn't make sense, yeah, because because I could not make something like 1.1. It contains some natural noise because it contains precision. Yeah, so kind of, and when you're trying to use all information which you have, all to the very, very last bit, what you do, you also contain information plus noise. And so naturally, you always need to decide how much information you want to regain. Yeah, so how much you're saying that is really important and how much is good enough. And the good enough, again, you can play the same game as we played with the overfitting, underfitting. You can take one component and do the prediction, two components and do a prediction, three components and make a prediction, four components and make a prediction. And you can build the overfit, underfit graph because, you know, if you use the PCA as the feature embedding or as the feature transformation for your input data. So you have your x's, but you replace those x's by PCA components. So you have a 10 x's, 10 or 10 input values, 10 PCA components input values. Yeah. And now you can see that, you know, if you take the first one, which will contain the most significant information. Why? Because it's just, you know, it's the largest eigenvalue of the covariance matrix. Because the eigenvalues of these covariance matrix, which are going into the which are going into the components of the PCA, they are ranked in magnitude. So the obviously the largest eigenvalue explained to you kind of it's a axis among in which data change the most. And afterwards, the next one will be a little bit less, a little bit less, a little bit less, and so on. And if you are dealing with a situation when you have several millions inputs, what you are going to see that for the generic data, not for some very specific, of course, we can engineer data where you know this distribution in the variance will behave like, I don't know, some sort of the power law with a very fat tails. But very often the distribution of eigenvalues in the very large data will behave like exponentially. So you have several eigenvalues which are very strong, and afterwards it's going down, and you have a very, very, very large tail, but very, very small of very, very small values. In principle, they could matter, but in practice, it could be noise. And so you can say that, okay, so I'm happy with, you know, the percentage of the variance. If it's above 1%, I'm going to take it into account. But if it's below 1%, I'm going to ignore all the components. And that's the logic behind. But if you wanted to find exactly how many components you need to take, first of all, you need to do the experiments. And secondly, you can really plot like, you know, training vs validation loss as the number of the components and see how does it perform. Have I answered the
Okay.
question? Mhm.
I hope they're answered. Lisa, please indicate if you're answered.
Or
And
have I
then we
got the
will,
question?
yes, then we will take a 15-minute break and resume at 11:15.
Okay. Do we all have a nice break?
Yes, we can resume now.
Uh, this is happening when I'm... okay. Yeah. Canvas also need to undergo sometimes a scheduled maintenance, or even an unscheduled one. Okay. Where we are. Oh, sorry, I was opening a carpet for something else and I lost my slides. Oops. Mm, okay. Screen. Okay, good. So let's continue our wild run. Okay, so the last bit which we're going to talk about will be related to the neural networks, and that will take us the remaining part of the lecture before the lunch, I assume. So, oops. Okay, so brief history. We need to do a little bit of history. Yes, so it's started with this famous perceptron model of the McCulloch pits. Yeah, and it was like, neuron biologically motivated models. Afterwards, there was the first implementation of the perceptron by Rosenblatt. And there was another famous result, which ended up with something which is called first AI winter, because afterwards, everybody was very excited that, that you can use a perceptron for everything. But in 1969, famous Marvin Minsky with the co-authors, they have shown that, perceptrons cannot learn the XOR function. And this was kind of a shock that, that such a simple structure could not be learned. Okay, but and the people forgets about neural networks until and only kind of the few people keep working on it, and first of all you get, and now we see that kind of in 80s famous Jeffrey Hinton, Jan LeCun, and others are joining the or kind of the continuing this work. So, and it was first it was the representation learning result by Hinton and co-authors. Afterwards, there was an even more interesting suggestion coming from the Jan LeCun, which is related to the structure of so-called convolutional neural networks. And that is a very interesting structures, which we are also going to talk about, and I'm going to mention just now. And 1995, there was a so-called LSTM, so kind of very specific form of recurrent neural networks, which essentially recurrent neural networks are used for um, text processing, or it's also used for time series data or kind of and things like that. But they have some problems, and the solution to that problems, which is related to the so-called vanishing and exploding gradients, was these LSTMs, which was on some stage the state of the art of this type of neural network. But of course, now we have much more interesting and powerful architectures. And what happens? Yes, kind of like, first of all, in 1998, on convolutional neural networks on MNIST dataset. MNIST is those handwritten digits, which we've seen already with the PCA and TSNE. So it was reached the first human level performance on a digit recognition, and that wasn't too bad. But the real breakthrough in the world of the neural networks and the convolutional neural networks happens in 2012. And essentially what happens in that instance, there is a very famous data set, which is called ImageNet, and this competition were running for the years, and now it stops. Because there was no need for competition, neural networks and these architectures wanted out of the blue. And ImageNet, as I mentioned to you, is a bunch of images with 1,000 classes. Essentially, it's like, horse, dog, car, house, and so on and so forth. You can just Google ImageNet, you'll get to the ImageNet website, and they have data sets with a detailed description. And what happens in 2012, that the AlexNet architecture by Krzyzewski, Schutzwecker, and Hinton have surpassed the closest competitor, I think, by 10% in accuracy. It was like, it was very incremental improve. And these people with the new architecture, they make just a leap in the performance. And afterwards, within the several years, next year, there was another convolutional neural network architecture, which was coming, I think one was coming from Google, one was coming from Microsoft, and so on. That every year it was better, better, and better. And on some stage, this ImageNet competition lose its reason for existence because the modern architectures of convolutional neural networks can reach extremely high accuracy, and there is no need to compete anymore. Essentially, yes. From the point of the ChatGPTs and things like that, the crucial event was in 2017 when the transformer architecture was proposed. Yeah, and because GPT is a general pre-trained transformer, so it's this kind of architecture, but modern version of those things are those things on the steroids. Yeah, and in 2018 there was a Turing Award, which was given to the Hinton, LeCun, and Ian Benjo, and so on and so forth. And you also know that Geoffrey Hinton get a Physics Nobel Prize in 2024 for his works on neural networks and the restricted Boltzmann machines. Okay, and yes, restricted Boltzmann machine is just another type of architecture which we never spoke about in this course, but it's also built into the standard neural network packages. And so if you're curious, you can just Google, and it's implemented, I think, I wouldn't be surprised if it's a part of scikit-learn. We can just give a look during the tutorial. Okay, but what I want to mention to you, interestingly, in what really happens and why convolutional neural networks were so powerful, so that in these old days and also up to here, essentially what was happening, there was a whole slew of the direction of computer science or machine learning or artificial intelligence study, whatever they were called, which were designing filters. Filters mean a mathematical operation, which we're going to see soon enough, which were built to recognize certain features in the images. Like, for example, you have an image with something, as with a house, and you build a filter, you handcraft some operation which can recognize corners, or which can recognize, for example, if it's images of people, eyes on the images, or noses on the images. And this is obviously a very tedious exercise, and it's very difficult to craft these features. And the people make a profession of making, kind of being very good in designing filters and so on and so forth. But what's convolutional neural networks by design are doing, they just say that, oh, we have some filters, and the form of the filters, you don't need to predefine them, because you getting them trained during the training procedure. So you automate the design of the filters, and the filters are designed as to represent well enough, or to migrate your input image data into some multidimensional space where you can do the cuts and you can do the linear separation, I don't know, between cats and dogs, or what is so catty in the cats and what is so doggy in the dogs from the point of the picture of how to design filters like that. It's completely outsourced to the training algorithm, and that's why neural networks are so efficient in this kind of tasks. Okay, so why this becomes possible, this real breakthrough in 2012, and this was a real breakthrough, and there is a reason. Number one is the gaming industry, which create a huge progress in the development of the graphical processing units. And the graphical processing units, or graphic cards, is the thing. In order to play a 3D game, what you need to do, you need to do the physics of your artificial world. And the physics of your artificial world means that you need to do the matrix multiplication. You need to rotate matrices of rotation, calculate how the light propagates, and so on and so forth. So what is the effect of, I don't know, throwing something and things like that in the 3D world? And this is a lot of matrix multiplication. So graphical cards get, by design, being optimized to this type of procedures, to a lot of linear algebra on the graphical card. And what the Hinton and others on some stage before that realized that the very efficient training neural network algorithm, which is called backpropagation, could be boiled down to the multiplication of the matrices. And now you have a graphical cards, which are very good for multiplying of the matrices for the gaming industry. And now you have that you also need to multiply matrices for the purpose of the training of the large neural networks. Yeah, and so these things goes together very well, obviously, and that's why now the main purpose of NVIDIA is not producing the graphical cards for the gaming industry, but producing the graphical cards and the computational servers for the AI. So, but they started as a kind of as a gaming industry service. Okay, so next thing. So you need GPUs to do a lot of linear algebra that you got in the 2012. Second, you need a lot of images. You need a lot of data. And the 2012, we are already far in the world of the internet where we have a lot of data. So we have a lot of images. For example, ImageNet will come with the images, but you know other thing for the text processing, you need to have a lot of digitized text and so on and so forth. So we get this. And of course, as the people begin to play the game of training neural networks and they see that there is a bottlenecks in the training, they begin to design better algorithms. So you get, different versions of the gradient descent. Instead of gradient descent, you get this SDG, so which is a stochastic gradient descent, and the stochastic gradient descent where you don't use the whole data, you slice the data into the training process in the small groups, which are called mini batches. You use and that works particularly well. You use, I don't know, different optimization techniques that you not only use the gradient, but also acceleration of the gradient and so on and so forth. Or velocity of the gradient, so which is acceleration. Yeah. So, and essentially, there are several things which come together, which makes the neural network revolution possible. And, you need data, you need the compute, and that we have now. And of course, we also get enough algorithm because now we have it. And the modern perspective on essentially on the algorithms, on why neural network works, and that's also is shifted also, for example, to the quantum machine learning, is what is called differential programming. And it means that you write the functions in such a way so that you can, if you have a function which calculates something, and it depends by the parameter, you can very easily calculate the gradient of your function as the programming routine, essentially. And when you have the tools which are building in that procedure, it makes the procedure of constructing all sorts of gradients, which you need for the training procedures, much more efficient. And that's what's one of the ideas of the differential programming. And of course, a lot of money from the companies. Okay, so what we need to think about that the neural network is not just one model, it's a family of models, and optimization procedure is done by the very specific algorithm, which is called backpropagation for the calculating the gradients, and that's what allows you to do the training. Okay, so the most simple neural network we've seen already, and it's essentially a perceptron, or it's a logistic regression, but with a little twist. So feed-forward neural networks is a model family, for example, for the regression problem, which could be written like this, where W is the matrix, beta is the vector, and G is a special function, which is called activation function. Okay, so you have an input X, which is a vector, or it could be input as a matrix, but for simplicity, let's start from the vector. It's getting multiplied by some matrix, which is given to us a vector, yeah? So, and afterwards we apply some function, which is called activation function or nonlinear function, for example, sigmoid, and how it's applied component-wise. So if we have applied to the vector z1, z2, it's applied g of z1, g of z2. And after this vector, it's also a vector, is multiplied by some other vector, and you get a number, yeah? So this is the simplest possible model family of the feed-forward network, or this model is the modern version of what is called perceptron. Okay, so what are the parameters? Matrix W is D by K, and of course, and beta is a vector with a K component. And of course, that implies that your input data have D components, yeah? And the K is the number of what is called neurons, or it's a hyperparameter which you can play with. Okay, and the activation function, which I mentioned to you, we've seen it already. It's one of those, is called sigmoid. Okay, So that we've seen, and what is the beauty of the sigmoid from the practical standpoint, that it can take any number from minus to plus infinity and convert it number from 0 to 1. Okay, so, and how you can see the feed-forward neural network. So you have an input vector, yes, x1, x2, x3. So next, you multiply it with the matrix. For example, the matrix you could have 4 hidden neurons. Yeah, it means that your W matrix should be matrix 4 by 3, yes, so that you can multiply it matrix with on the 3-dimensional vector. Yeah. And afterwards, you apply to each entry of this multiplication, you apply activation function. And now these 4 neurons, you sum up with the weights beta 1, beta 2, beta 3, beta 4, so that you get a number. So this is a very simple feed-forward neural network. And why we need to use a sigmoid or something like that? So because what happens if the G is linear? If it's a linear function, we just get back to the linear regression. Yeah, so if this is a linear function, it means that it's just working as the multiplication coefficient, and this we recover the linear functions. Okay, so that's why nonlinearity is crucially important, because nonlinearity, what essentially the fact of the presence of nonlinearity, the presence of the layer of the hidden neurons, this number of these extra neurons, and we're going to see that you can have also extra layers, is that what give the power to the neural networks, that on every step you do nonlinear transformation, you spread your information, nonlinear transformation, and afterwards you spread your information and you do correctly your information. That's what give the power to the neural networks to recognize the patterns. Okay, so classification. So that's clear that would be solving a regression problem. And with the classification, yes, we're recalling that for the logistic regression, we have something like this. So it means that, just a sigmoid applied to the input data. So it means that now we have one activation function, and also we need to add one more activation function on the output. And in that case, it works like a classification problem. Okay? Multi-class classification in the same way as we had in the kind of a traditional machine learning algorithm, we just do a softmax. So it means that we do e to the z1, e to the z2, e to the z3, and take an average of those, or take a ratio of those, e to the z1 on the sum, e to the z2 on the sum, e to the z3 on the sum, and this is 3 probabilities of the corresponding classes for the multi-class classification. Okay, so historically, there is a historical and modern view, and we will go with the modern view because this is much more efficient and nice view, and that's how the logic of the pattern of the modern packages is built in. Yeah. So historically, it was this type of network, that type of network. There is a convolutional neural network. This is one chapter in the book, or one set of families. The feed-forward dense neural network, it will be another chapter, or perceptron will be another. But essentially, kind of like each new model is requiring new architecture. But in fact, you can very easily abstract it away, and you can see it as the neural network is the object which is built out of the building blocks, which are called layers. And there is a laws how you need to compose those building blocks together. Yeah. So in the building blocks are layers, and you can implement these layers programmatically. Yes, and in the Python notebook, which will be in the canvas soon, it's just, how we're going to build it. We're going to add this type of layer, that type of layer, that type of layer, and that's all. We're not going to write a specific structure for this type of network or not. We just add the corresponding layers which correspond to the architecture. Okay, so historically is what I told you, but now from the modern perspective, it could be written like this. So in this little symbol, this little circle in mathematics is called composition operation. Yes, so which is applied successfully, and so that you can see it that your first option is your input layer, which is your input data. Afterwards, what do you have? You have a multiplication by the matrix W. This is one more layer. Next step is, which is kind of, and composition is applied, from this side to the whatever is coming in front of it. or to whatever is coming on it. So f of w is applied to x, g is applied to whatever is standing here, and f of beta is applied to whatever is standing here. So, and essentially, it means that we have input layer, we have a layer of multiplication, layer of nonlinear function or activation function, and layer of multiplication with the vector beta to get the output. So this is just a formal way of writing it, but essentially this way of writing it, it's immediately give you what is the recipe to scaling it up. You just add more compositions. Instead of writing multiple brackets and you can be lost in the brackets, you can just write the multiple compositions. Yeah. So each layer is some sort of a function from k-dimensional space to h-dimensional space, so that you need to take careful look into the dimensions. Yes, and it's kind of the typical neural networks are composed sequentially. While it's not necessary, you can compose it non-sequentially. You can have branches, and afterwards you can have reemergence of the branches. But the typical and the standard way, or simplest one, are the sequential layer after layer, which you can write as a composite function, but it's much better to use the composition notation. So this means that, in this way, it's going to be m layers, whatever this m means, and it will have a meaning within the architecture. Okay.
Sorry, Ilya. Can you please paste the code for the neural exercise, because Canvas is down at the moment?
I'm not sure.
So the code for the neural networks, right?
No, but I mean the code I'm planning to upload during the launch. We don't need now the code.
Yes,
But,
just in case Canvas is also down after lunch, because it's
okay.
not
No, but in
working.
that case, I will do it in the chat. Do you want me to do it now, or I mean?
I know, I was just suggesting
Okay,
that we put it in the chat also.
okay. Just
Yeah.
because what time is the lunchtime? 12:30, yeah.
Yes, 12:30.
Okay. No, but I mean, let me put it at that instance, unless people want to start already playing with the code. But I don't know. People
Okay.
can.
All
Okay,
right.
so how to go back? uh, Sorry. No, I lost it. Here it is. Okay. So each layer have a bunch of parameters because, if we multiply that by matrix W or multiplying by the vector beta, it will be all the parameters, yes, which requires some training. We can compose layers in other way using the concatenation, yeah. So, and in that case, that could be, so we can do it composition, but concatenation is exactly adding things like this. So if layer by layer is layer by layer, but if you want to have two branches, by whatever reason, for example, your input data have some structure, for example, it's an image plus something else, and you might want to mix it a little bit, but afterwards you want to process it separately, and afterwards you want to remix it again. So you might want to use also concatenation. So it means that it just it's extending it. But again, with all the standard packages, as you're going to see, this model is called sequential, but there will be there is also other models supported. Okay, so let's go simply, yes, kind of like into the simple sequential step first. So we're doing the feed forward. So again, for regression from the modern perspective, this is just a composition of the three layers. Yeah. So first multiplication by W of the input, afterwards nonlinear function, and afterwards multiplication by the vector beta, and we're going to get it as for the regression. Or you can also draw it like this, because then we will need that nice drawing for our training algorithm. Yeah, so we take x, we apply fw, we get vector z1. Afterwards, we apply nonlinear function, we get a vector z2. And afterwards, we apply f of beta multiply by beta transposed. We're going to get a number y, which is output. And this is the input layer, this is the output layer, and this is all hidden layers. Okay, yes, so kind of that's, yeah. So we have a hidden layers, input layer, output layer, and hidden layers. These guys are called nodes or units. And these are called weights because, and when you, for example, can download the pre-trained, AlexNet or ResNet from the TensorFlow or PyTorch package, that's exactly what you're downloading. You're downloading set of matrices, which also by this dimension, they know how to fit to each other. Okay, so now, if you want more layers, or kind of more of this matrix multiplication W, that's how you're going to have. You start with the input data, matrix multiplication, nonlinear function, matrix multiplication, another nonlinear function, and now it's beta. Yeah. So you can write it like this, but this is much more fancy way of writing it. And of course, you can extend it as much as you want. Yeah. So what are very nice things about the neural networks? So that you're designing the whole family. The models are describing to us the whole possible families already of the models, which is very nice. You can, within this design, you can embed structures or symmetries in your data. For example, if it's a science-driven data, for example, if the input is, I don't know, many-body ground state, yeah, and if it's a many-body ground state of fermions have some symmetries, and you can embed it on the level of the structure of your matrices, such that the symmetries of your input data will be respected. Yeah, so kind of like you can embed these things, which are very important, and or for example, there is another thing, okay, but I will mention it later, which is related to what is called geometric machine learning in the end when we're going to talk about the data augmentation. Yes, and there are a bunch of positive things, but there is also problems that, very often we have a problem with the training, and energy landscape for the neural networks is exactly what is called non-convex. It means that, they are very, very hilly, and in the training, you can really easily stuck in the local minima and never get to the global minima. And that is a purely computational problem. Lots of parameters means you need a lot of data to train, and you have too many options. Sometimes with the neural networks, one of the problems is that there is too many options. You have written a small neural network and it's performing okay-ish, but you want to better. And now the question is, what else can you do is too long? Or you can add more layers. No, you can add more layers and you can increase the number of the layers in the corresponding layers. Or you can change the different activation functions. Or you can, I don't know, introduce the batch normalization after each layer or after the second layer. Okay, you can introduce what is called pooling layers and things like that. So there is so many options. So sometimes it's a little bit overwhelming. And it's kind of the good case is just, you just do experiments and you need to find, your way of navigating these families of options. Okay, so now we're coming to the how to train neural networks, and this is the kind of the wonderful idea of the Hinton and co-authors about what is called the backpropagation. Yeah. So based on the gradient descent, there is a few tricks, yes, because backpropagation is using the gradient descent, but in a very smart way. So the problem is that the loss is non-convex, but the practice is showing that the gradient descent or gradient descent based ideas work well. So, and the key problem is how to compute gradients, because you have so many parameters, you need to compute gradients with respect to all of that parameters. Yeah. So, and the kind of the breakthrough is that, you can compute it essentially in one go. And this one go is called backpropagation. And how the backpropagation work we're going to discuss just now. But the idea essentially, the gradient descent is the same gradient descent as we have before, but now we need to have it for the same kind of for the layers or for the parameters of the neural network. So we have some initialization, and until convergence, we are going to play the game of updating the weights in the corresponding metric, so in corresponding vector by the following simple rules. Yeah. So kind of like we take the previous value and go into the opposite direction of the gradient, which is calculated with respect to the corresponding weight matrix. Okay. And now kind of by doing this until convergence, we can reach some result. But the secret of the backpropagation algorithm that you can calculate all the gradients with respect to the all parameters essentially in a single passage or the single reverse passage of the backpropagation. Okay, so what is the backpropagation and how does it work? So we have example, yes, input and label, yeah, or input and kind of the value. We can have an example, input image and cat, dog, class 1, class 2, yeah. So we have some model, yeah, which means that, M stacked layers or M composed layers. We have some loss function, and loss function is dictated by the type of the problem which we are solving. So we can what we need to do, so we can calculate obviously derivative with respect to our loss function, because we can do it kind of analytically and implement it programmatically. And in principle, what we know programmatically, or not programmatically, but analytically, how to calculate derivatives with respect to each of the layer, and I'm just going to tell you just now, and with respect to every operation, because it's relatively straightforward as a function. And now what the output will be of the backpropagation is the gradient of the corresponding parameter for the corresponding pair. And it's going to be done in a very efficient way, computationally efficient way. And that's where you can turn this problem into the matrix multiplication. And how it's done, that's exactly the backpropagation algorithm. So in order to calculate the gradient, first we need to remember a little bit of calculus and remember how to calculate the multidimensional derivatives. And afterwards, we will need to know how to calculate the derivative with respect to the composition of the functions. Or how we can define what is the derivative with respect to the z of the matrix. Okay, so what is derivatives? Yeah, first of all, let's memorize a little bit. Kind of like the derivatives we can define from the very simple. Yeah, so if we have the function f, which is parameterized by the parameters w, and if it's function f of z, we can do a Taylor expansion, which is going to look like this. Yeah, and up to the first order, and the first order terms exactly is going to give us the corresponding derivatives. Yes, if we subtract functions from here, that's how we can extract in principle the corresponding number. Okay. So for example, if we have a gradient of MSE loss for regression, and we've seen it with you already, at least for the linear regression, how it could be done analytically. What is the gradient with respect to the parameters of the matrix of this function? It's going to look like this. Yes, so we're going to take a derivative of the function, yes, and that will be 2 divided by n blah blah blah, and afterwards derivative of the subfunctional expression. Yes, so it will be derivative of the f of w beta. Yeah, and the same but derivative with respect to the w. The same for the derivative with respect to the beta. We take a derivative of the function, of the composite function, so it's derivative of the quadratic function, and afterwards, which is a 2 on the function, on the derivative, and derivative with respect to the beta. Okay? Now, it's more interesting that's how the derivative of the neural network could be calculated. So now, if we calculate a derivative with respect to the beta of our neural network, it means that we need to calculate derivative of the beta of this thing. Yeah. So because beta is the first thing, it will be just derivative of the f of everything else. Yeah. So it's easy. But now, when we need to calculate the derivative by w of our neural network, again, we have our good and humble composition rule. Yeah. So we have derivative of the w with respect to this. It will be derivative of this function with respect to everything which is standing underneath, multiplied by the derivative of this function with respect to this. Yeah. And now this guy will be the derivative of the activation function, which we can pre-calculate. So we know what is the derivative of sigmoid, for example, is. Yeah. And we get something like this. So derivative with respect to the parameters of the kind of deeper sitting inside of the layers is just will be the product of the corresponding derivatives. And now is a very simple thing why it's all work very nicely. Because what is the derivative of f of beta? Yes, with respect to whatever is coming underneath. It's what is the f of beta? F of beta is a beta multiplied by vector. So derivative with respect to the parameters beta will just spit out your corresponding number because it's just a derivative linear function. The same is derivative of your activation function, derivative of the sigmoid. We can calculate in advance, yes, or derivative of any other activation function, and we can implement it programmatically. And what is the derivative with respect to the parameters of the matrix multiplication? It's a matrix multiplied by number. And what is the derivative when you multiply it? We just get some linear expression. And what is the derivative with respect to that? It's just, again, a derivative of the linear function. And it will just give you a coefficient in front, which means the corresponding x entry. Yeah. So, and this could be done in a general way. So if we have a f of w, it's some neural network, which is a composition of m layers or m compositions. Yeah. So what is the zj? Zj is the intermediate value on the j step. And if j is 0, it's input x. And if j is greater than 0, is f of wj to apply to the zj on the previous step. So how would you calculate the derivative with respect to the Wm? It's a Wm, f of Wm on Zm minus 1. What will be the m minus 1 derivative? Yeah, so first we need to differentiate Wm, which is acting on everything. And now we need to multiply it on the derivative of m minus 1, acting on the from f of m minus 1. Yeah, and that's all. And so that, and you have this nested multiplication as you go down by the chain of m minus 2, m minus 3 till w1, you're just going to have this nested multiplication. But if you now just give a look into the previous step, yeah, so what is the derivative of wm with respect to this? So we need to differentiate this function. Yeah, okay, here's with respect to the wm, but the intuition is that here we need to do a very similar procedure. And so we can in principle use data from the previous case in this case. And that's where kind of the calculation in one go is coming from. So Wm minus 2 is obviously absolutely the same thing. Wz to the derivative with respect to this layer, which acting on everything. Now the next step is the derivative with respect to the previous layer and multiply by the derivative of finally of the layer, which we need to differentiate. Okay, so derivative with respect to the arbitrary layer would be just corresponding composition, yeah, of the derivative of the deeper into your hierarchy of layers. Sorry, there is a question. In the modern view, why isn't a sigmoid function applied to result of layers to get a single value? I'm not sure that, but I mean, if you apply sigmoid to result, now I mean, it depends what kind of problem I'm solving. Of course, you can apply sigmoid to the result, but sigmoid to the number will give you a number. So if your output is a bunch of numbers, like in some intermediate layer, you still need to bring it to the one, and that's why you need to multiply it by beta. And the sigmoid was used there just a last layer if you want to solve the classification task. But if you solve the regression where you know that your numbers are between 0 and 1, you can also do sigmoid. But because regression is not necessary as a number from 0 to 1, it could be number from minus 20 to 20 or from minus from 0 to a million. So sigmoid in the end will shrink it from 0 to 1, and you need to have a method how you can unshrink it afterwards. If you want classification, you want a sigmoid in the binary classification. If you want a multi-class classification, you use a softmax, which becomes a sigmoid for the two classes. Okay. So let's go back to our backpropagation. And the idea here is really, it's a very interesting idea, so that, it's really kind of like, we know all the derivatives in advance. We don't need numerically calculate derivatives, which is very important because, in the moment when you need to replace, when you need to numerically calculate derivative, you need to use the finite differences on the lattices, on the corresponding discretization, and it's done with a certain precision, and the precision is, you need to choose and so on and so forth. And kind of like if you have a lot of layers and you need to calculate these derivatives approximately, your error will just multiply, and you don't want it. So you don't want a huge error. Yeah. So, and that is why all of these intermediate steps we can do analytically. Yes, because what is a derivative with respect to the parameters? This one of the, I don't know if it's a matrix multiplication, is just a corresponding entry from the z. Yes, because you're just differentiating linear function. Derivative of the activation functions, we know what is derivative of the sigmoid, we know what is derivative of the tanh function, or ReLU function, or Lickler ReLU function, or whatever any other activation function one is using. Okay, so if we denote all of these derivatives by dg, so we can compute this dg recursively from j is equal to m to j is equal to 1 by a very simple operation. So yes, if j is equal to m, it's just 1. If j is smaller than 1, it's just derivative of the higher order on the previous step. Oh, why higher order? If j is smaller. Okay. Okay, doesn't make sense. So should it be -1? Because M is in front. Yes, yeah. No, it should be j plus 1. Okay, good. So because this is not the order of derivative, this is just the order of the derivative in the chain. Sorry. Okay. Yeah, and essentially, how does it work in practice? So we have our neural network. Yes, we have a forward propagation path. So we have an input value. We apply the first, I don't know, matrix multiplication. We get another vector. We apply nonlinear function. We have another vector. We have multiplied by the matrix. We get vector. Another nonlinearity. We get vector. And now we multiply by beta, and we get a number, the real number. Okay, this is called the forward pass. Yeah, so we have input, we get some output, and now we can calculate the loss function. We can calculate how this y is close to the ideal y which is supposed to be. Yeah. And now what the backpropagation is doing, now we're going to calculate a backwards path to calculate the gradients in order to adjust the weight of each of these w, and beta in order to perform a next step of training. So what are we going to do? We're going to compute each of the derivatives with the corresponding things, and so that we know how the gradient is looking like. So we have here parameters, and here beta. So first we do the forward path. Yeah, so we calculate z1, z2, z3, z4. Boom, we get an answer. Now we are calculating d5. And in calculating d5, we immediately know what is d beta and f of beta. So we know these derivatives at this step. Yes, because we store these values. Now we continue d4, and in order to calculate d4, we need a d5, which we stored already. Yes, d3. Okay, here we don't go down because there is no parameters in this layer, because this is just a sigmoid or tanh or any other activation function. And now when we're at this level, we can calculate the derivatives, but we need this information and this information, which we already have. Yes, and we can store it or update the corresponding weights here. And we continue in the same way till here. And so now we have, as we go forward, we have done the calculation of the values on each step. And as we go backwards, we use the values into the corresponding derivatives, and we store we can store it in the matrix form. Okay. And now, yes, in the forward pass, we're computing, we're starting from X, and afterwards we're calculating each layer application. In the backwards path, what information do we use to determine which values to assign to our weights during the backpropagation? What information do we use to determine? No, but I mean, we don't assign any weights during the backpropagation because the weights we calculate while we're doing the backpropagation, we calculate the gradient with respect to each weight, so that after we have done the backwards path and we calculated all the derivatives, which were calculating recursively, because here we use the weights which are in, but we are kind of sorry, what this means. This means that we kind of like beta is a vector, yeah? Beta 1, beta 2, beta 3, whatever the number of inputs in this Z4. So what do we need now to calculate? We need to calculate derivative with respect to the beta 1, beta 2, beta 3 of whatever this thing was acted on. But this thing was acted on Z4. And we have these Z4 values, yeah? Because we have this vector. So, and what will be the corresponding derivatives? It will be just the derivative from the previous step, but in this step, there is no derivative, yeah? And the corresponding value of the Z4, which is standing in front of the corresponding beta. Yes, because because what is this step? What is Z4? Z4 is the vector. What is f of beta? Is the multiplication is by a vector. So we get beta 1, Z1 plus beta 2, Z2, beta 3, Z3, and so on. So when I need to calculate the derivative with respect to the beta 1, what will be the outcome? Because it's beta 1, Z1, beta 2, Z2, beta 3, Z3, and so on. It's a sum. So with respect to the beta 1, it will be just Z1. So it will be the first component of this vector, and it's going to be recorded. Because what I want to calculate a vector of gradient with respect to this vector, and that will be the first component of the vector of gradient. And so I just calculate all of them. On the next step, when we're going to go into here, it won't be only the corresponding value in front of the matrix element, but it also will be multiplied by the derivative from the previous step. And that's why we cannot just take these guys and write them in. Okay? So because during the backpropagation, we're not assigning any weights. We're calculating the gradient, and after we have done the backpropagation pass, we are going to update the weights with respect to the, for example, gradient descent. But in fact, nobody using gradient descent. People use, modifications of the gradient descent, like, stochastic gradient descent with mini batches and blah, 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 and other fancy methods. Okay. I hope that clarifies a little bit. Okay, so and that's exactly what written mathematically what I just talked through. So during the backwards pass, we're calculating the derivatives, which could be calculated in a recursive fashion. Yes, so kind of like to calculate the current derivative, you need to multiply it by the previous derivative on corresponding current derivative, which is applied to your particular data, and you do it recursively. And because you store the value of the previous derivative, you do it recursively. So in the final output will be just the derivative of your loss function, which of course like if it's MSE, you know what is the derivative of MSE, how it looks like, on corresponding derivatives with the corresponding layers, which was stored during the backwards path. So it means that we have a gradient. Now we can feed this gradient to the gradient descent and update the weights and do again the forward path and so on. Yeah, so now again, so we initialize W's, and that's a separate story how to initialize. So there is different initialization strategies, and as a function of initialization, your neural network performance will be different. So you have your weights. Using the backpropagation, we calculated this guy, and now we're just updating the weights. Yeah, so we update the weights and we get a new weights. So it means that we have a new matrices for our matrix multiplications or new vector beta for your output layer. Okay? So we've done that. And we do it for every parametric layer. Okay, and I think I skip it in this slide because it gets a little bit mathematical. But in the moment when you try to write down these operations on the level of the indices, what you're going to see that what it's all boiling down to, it's literally boiling down to multiplying of the corresponding matrices. So essentially, the calculation of this thing, I mean, this guy could be, if it's a derivative with respect to the vector. So okay, so this, what this will be? This will be a vector. What will be this derivative? This derivative will be a matrix, which will be multiplied by a vector. Yes, and so on, so that you can really see it as a stacked multiplication of the matrices, and that's why it could be very efficiently propagated. Okay, so now what can you do with neural networks very quickly? And that's what's coming from some practical things. Okay, so why you have a problem with optimization of neural networks? Because it's a non-convex, and this is optimization problem. We're not looking for a minima in the ideal ball. We're looking for a minima in the loss landscape, which look like this or even worse. So you might have some global minima, but you have also a lot of local minimas here and there, so that you can easily stack somewhere. Yeah, so it's a standard way, so that it's a non-convex optimization, and it's not solvable so easily. Okay, but there are some rules of thumb which one can use. So the first rule of thumb is, so we take our gradient descent and we want to play with this thing. So, and we want, instead of going for the, so we have a kind of like endpoints in the data set, we can now start to playing with this. So we can just calculate, for example, we can do a stochastic, what is called the stochastic gradient descent. So, and we can now play with the number of entries. Yeah, so we can divide it into the random groups of the input data and do the, first of all, calculation along the random axes and the calculation among the random subsets, and use that for a bit of propagation, which is not a full information, but the practice shown that it works a little bit better. So what else you can do? Because what is the gradient? Gradient is velocity of the changing of your parameters. But you can also calculate the acceleration in the change of your parameters. So you can change the velocity of change of velocity, so you can get an accelerated gradient descent. So you can make it faster as a function of how the system is behaving. And the typical, yes, kind of the intuition is that you can introduce an extra parameter, which is essentially remembers where it was heading down to. Okay, so you can have an accelerated gradient descent, or you can have what is called the Nesterov momentum. So you can begin to play games essentially with how your how your gradient is getting applied to. Okay, so and the logic behind the Nesterov momentum is so that in the normal case you have a gradient in one direction, momentum in another direction, and step is going into the average of that. But with the Nesterov momentum, you are going into the momentum and gradient, you are adding them like this. Okay, so kind of this look ahead avoids overshooting when you're close to optimum. Okay, so you can also have adaptive learning rates. So you could have the learning rates is changing as you go, or you could use some, kind of like you could add some function of how your learning rate is changing, or you can add some, exponential moving averages and so on. But essentially, it just giving you, there is a lot of recipes which you just need to try and play with the learning rates and with optimization. Yes, I mean the standard Adam optimizer is used kind of like as a default, and I think we're going to use the Adam one. And the intuition is that it's this RMS prop, which is essentially exponential moving average in the learning rate with momentum. Yes, and the Adam is the most common optimizer. Yeah. So what are we going to see about the learning rate? So that the loss is going to behave something like this. It's going to oscillate back and forth as the number of full cycles of training, which is called epoch. And what we're going Yes, yeah. So it goes forward, backwards, updates the weight, and start over again. Yes, when you have done the forward, backward pass over the old data or the part of data, that's exactly one epoch, and you do it as many times as you get. And the 100 epochs is a very small number, if you have a lot large data. So and you want your loss to look like that in the sense like it's going down. If you have a lot of data, it will be due to the noise, it will go in back and forth a little bit, but as long as you have trained down, it's okay. So, which is the typical scenarios for the learning rates? So if your learning rate is too high, your loss will look like this. So it means that you're doing something wrong. So if your learning rate is low, it will go too shallow down, it will go down, but too slow. High learning rate can also lead you to the behavior like this. And the good learning rate, so that it's not really exponential decay, but something like that. So it goes down fast enough, and afterwards, yes, you see how it's going. And this is the training loss. We're not even discussing is it the overfitting and underfitting issue. Okay. So learning rate vs training error, so that we have a training error and learning rate, and you can see that the training error with the learning rate is going down, and until it shoots up. Okay, and what the people do with the learning rate, they do the scheduling, and I mentioned it to you already. So, and essentially, it starts with the uh, high learning rate, and afterwards you decrease it slowly after a certain number of epochs, and afterwards you decrease it more and decrease it more and decrease it more. And people have done some numerical experiments, and they find out so that that you can reduce learning rate every time the validation loss stagnates, for example. So there are different strategies how you can change learning rate, and most of the packages have it embedded, so you can just play this game so that you have with your learning rate. So you can say that you can by yourself design a schedule, or you could have it done programmatically, for example, like it's suggested here, so that it's one of the approaches, so that when your loss or error do not decrease, you decrease the learning rate, and you see the jump in the performance or the reduction of the error, and afterwards you again like stagnate, and it means that you need to decrease it again and think like this. Or you could just decide that based on your experience, you can just see that, okay, but you see, look on this axis, iteration 1E4, it's mean that it's a 10,000, 20,000 epochs, 30,000 epochs, 50,000 epochs. So that this 100 of epochs is a very, very small number. In our naive, for example, we're also going to deal with that. But if you're looking for more serious training, you have millions of epochs essentially, or millions of these cycles. Okay, so that was a little quickly about optimization, about activation function. We've seen the sigmoid, and it's kind of like it looks like this. You can use a sigmoid and as the activation function. There is function which looks very similar, which is called tanh. It is also used as the activation function, but there are several other things, and in both cases we can very easily find the derivatives. Yeah. So the problem is why both of these guys could be not the perfect example of this problem of the vanishing gradients. Why you have this problem? Because we have a sigmoid which looks like this. The derivative of the sigmoid will look like that. Yeah. So, and if you're trying to calculate the gradient and your domain, the input into the gradient in somewhere here, you will get some reasonable number. But if you are here or here, you will get something very, very quickly, which is close to zero. So, and this is a problem. And you have the same problem with the tangent. So, and what are the solutions? The solutions are much easier than one thing. And people suggested it's called ReLU activation function, or kind of, which is essentially is X y is equal to x for the positive axis and 0 otherwise. And you would think that isn't it linear function? No, it's non-linear function because it's distinguishing between the positive and negative inputs. It's have a very simple derivative, yeah? So it's 0 for the negative numbers and 1 for the positive numbers. But in fact, practically, it works very, very well. Surprisingly enough, if you use it, no, we don't. If you use it, essentially, the standard recommendation is that you use ReLU for the internal layers. And, practice have shown that it works extremely well. And that's why, people stick to it very strongly. So, and what does mean the practice have shown? People have done an experiment, they use a TANCH and they use a ReLU, and the ReLU is converging much, much faster. The training is happening much, much faster. There is a version of the ReLU, if you don't want 0 in the negative domain, you say that it's not sensitive enough to the whatever the input data you have, you could have a ReLU which is a combination of two linear functions, but with a different, of course, coefficient of linearity. So this is y is equal to x, and this is some quite shallow y. So it's not 0, but it's negative such that it's behaving like that. So and it also works well. Yeah, so ReLU is a good. Yes, and there are new activation functions that people are still proposing. So you can always try and see what's happening on your data set or how the system is behaving. Okay. So now managing weights. So now the first thing is, I told you how to update the weights. And let's pretend that, we understand how to update the weights. But, the question is, where should we start with the weights? Yeah, because we need to start somewhere. And, the naive choice is, for example, we can start with zeros, but it could be a very, very, very bad choice because we're going to multiply by a lot of zeros. Yes, and if you start with the equal, so that also the gradient, so you can say, oh, we can start with zero, so we can start with ones. But also the problem that because they kind of the same numbers, they can be start equal, and that the gradient could be a little bit weak. And sometimes people start with the random, so you can have a uniform random numbers, or you can have a Gaussian distributed random numbers, or something like that. And I think yes, so there is a bunch of numerical experiments people have done, and they have seen what works good and what works not so good. So the long history of initialization trick is based on fun-in, where the d-in is a dimension of the input layer, and intuition keeps layers in the linear part of the sigmoid initialized intercept near zero. So there is this, for the ReLU activation function, it's used the Gaussian random number with the zero mean, and the variance is 2 divided by the dimension of the W. And there is another Habiak initialization, which works well for the TANCH activations. It's again Gaussian random number with the standard deviation d in plus d out. Yeah, so but it's like, people have done experiments and they see that seems to be working. That's why now we have this initialization and that initialization. You can always do your experiments and see what works for your architectures. Okay, so there is one more little problem which is addressed now on the level of the specific layers, which is called batch normalization. So problem is looking as the following. So when you train, yes, during the training, the distribution of the input at each layers are shifting. So, and kind of like, and what's happening to the distribution of the layers is just kind of maybe it could be drifting to the side. And so what you want to bring it down and bring it back to the being kind of the, like, that numbers which are coming from the normal distribution. And this procedure is called batch normalization. And this is essentially, the extra layer which you can add. Okay, and again, why I'm talking to you about that? Because, people have done a whole bunch of numerical experiments, and these are experiments with the much larger neural networks. And you see, because you see the number of epochs here is in millions, and you see that, when you have with the batch normalization, the number of training steps is smaller than, without. And that's why people say that it's a good idea to do it. But you can do it without, see how it works, and afterwards add it. Okay, so you can also do the games of the regularization. So we can use L1 or L2 as before. Yeah, so L2 is we're kind of we're doing just extra, we're adding extra sum to the optimization to our loss function, which is looking like this. And corresponding norm for the matrices, it's called the Franibius norm. Okay, so essentially there is, again, what we need to practically get from that, it's not that, so kind of like when you have your vanilla neural network and it's working and you give you some results and everything works fine, or everything works okay. If everything works fine, you don't need to do anything. You just need to do, I don't know, k-fold cross-validation to have your distribution of the mean accuracies so that you can have a mean accuracy and what is called the deviation of that so that you can report it. But if it's not working fine, now you need to play with optimization. What will be the sizes of mini batches and so on. You need to try to play with activation function. You need to see what's happening to the activation of the weights. And that's why, it's a little bit overwhelming because, we are going through this and there is a few more very basic tips and tricks, which is just giving you just too many options if you think that you need to apply it for the large enough neural network. So now dropouts. So dropout is also a very nice idea, which is related to the fact that sometimes during training, just because of initialization or because of the combination of random initialization plus some random distribution in the data, some part of the neural network learned something stronger than the others. And now it's prevent others learn more information. And so essentially, what do you want? You want that the information which you want to learn is more or less equally spread around within the layer. So, and how you can enforce it? You can add an extra layer, which is essentially, what does it do? It's randomly turning off several neurons. Randomly. It's just randomly saying that, this, and this connection is turned off. And on the next run, it will be randomly turning off other. And so as a result, the remaining part of the neural network have to learn information or relearn it, but in such a way so that you are getting much more robust distribution of the whatever you are trying to learn. And in the kind of like convolutional neural networks which are dealing with the images, you can have a dropout layers, not only 50, but you can have 80% dropout layers, and it's still working very, very well. So this is just a scheme. You add in dropout layer, and it's mean that half of the neurons on each layer of training, and which half is determined by the randomness, will be turned off. Okay, so dropout intuition, it's a form of regularization or whatever I told you, so that it's forcing the information to be learned distributively, not that by it's some separate path in the network, and so that it's learned some bit of information but could not generalize or could not learn it better. Okay. Okay, yes, it's encouraging robustness to the missing information from the previous layer. Each neurons work with a different kind of inputs and so on and so forth. Yes, you can think it partially as ensemble in some sense, so that different hidden neurons you get a contribution from the different hidden neurons, and you have a lot of random neuronic paths, so that you can think about that this is some form of ensemble which is like built into the neural network structure. Okay, so drop out at the test time. So naive strategy, which is always, it's kind of dropping neurons, and not the problem is that the distribution layer was not trained on, and you can get a covariance shift. So average across of all possible predictions. So there is a 2 to the n possible realizations, where the n is the total number of neurons. And kind of like, if you get a problem with your dropout, so essentially what you need to do, you need to try to slash weights by 2 and so on. So kind of there are different suggestions. But dropout layers, especially for the neural networks which are dealing with the things like image information, it's really necessary. It will really work better. And the last bit is managing training. And managing trainings mean that that you need to not train till the number of epochs you say, but you can devise some stopping criteria. So, and this is called early stopping, and it's built in a standard way. So you could have a different stopping criteria. For example, you could have a stop criteria when the validation loss starts increasing. Yeah, or because otherwise, because this is a typical example. So we have a training loss, it's going down, and you see it's getting very low, but the validation loss is going down, and afterwards it's stationarized a little bit, and afterwards it's begin to grow. And essentially, this bit of training, which is from epoch 50 to the epoch whatever 240, is unnecessary in principle. Yeah, so and it would be nice if your software would have stopped here. So and this is called early stopping criteria, and you need to say exactly, what is your tolerance for stop. So if at the next training, I don't know, the validation loss have increased more than X or haven't decreased more than X, you stop. Okay, so one more thing is approach, which is called data augmentation. And I promised to tell you a story about the geometric machine learning where you don't need a data augmentation, but it's a little bit more difficult thing to do. So what is a data augmentation? Data augmentation is if you don't have enough data and you always need more data. Yeah, if you don't have enough data, you might want to try to tweak your existing data so that it works well. For example, if we have an image of the cat, yeah, if we twist it a little bit, rotate it a little bit or reflect in the mirror, it's a still image of the cat. Or if we zoom in a little bit, but from the point of the algorithm, it's a 6 different images or 7 different images taking the original one. So from one image, we managed to produce 7. So essentially, if we do it for every entry, we increase the number of points in our data set 7 times. And if you have, not enough images, if you have, 500 images of the cats and 500 images of the dogs, so you can turn it into the 7,000 images data set, which will be a better fitted for for example, neural network training. And again, data augmentation, a random rotation on which angle and so on and so forth. And okay, so and what is interesting with the data augmentation is that there are neural network architectures, which what I managed, what I told you in the beginning, that the neural networks allow you, if you are using it the right way, it's allowing you to embed symmetries and structure by default. From mathematical perspective, rotation of the image is operation. Yeah, and so you can design a neural network layers which are invariant or which doesn't change with respect to the rotation. So it will be a very specific type of layers. They will have a lesser number of parameters, but you can embed these data augmentation tricks on the level of the structure. And these approaches which embed what is called symmetries, or you can have a layers which are flipping invariant. So with respect to the mirror reflection invariant or respect to rotation invariant. So you have a much less parameters, but you have the same power of the neural networks. They will be easier trained, but you have some other issues with them, or they're much more difficult to implement. Okay, so and now we spend a little bit of time. Okay, we almost don't have time on how the convolutional neural networks works, but okay, you can just give a look very quickly. I mean, what is the image? Image just is bunch of numbers which are meaning the grayscale of the from white to black or from white to black. Yes, and the 3D images is that a 3D arrays of the same thing, which is just telling you the corresponding intensities of RGB. Yeah, so we have image, it's a bunch of numbers, and we can have some, and some images have the translation invariance. Yeah, so if we can move it a little bit, so that can be used for the data augmentation. Yeah, so beside the translation invariance, there is also translation equivariance, which is used for the object detection. Yes, and now, yes, we're coming to the layers in the convolutional structure, but I think I'm slowly running out of time. Yeah, let me try to run quickly through this. So, Tutukili, what is our schedule for the afternoon?
We have two more sessions. Let me confirm. Yes, we have two more sessions from 1:30 to 3.
Okay, so we'll have 1.5 hour, and that's all.
Yes, yes.
Okay. Now I think that I need to finish here in that case, but in the afternoon that I will very quickly run through this, and we will also give a look into the notebooks because one notebook the students can already see. Okay, let's not rush through this because this is also an interesting thing.
Yeah. Yeah, I
Okay,
think let's take a lunch break now and we
yeah, because there
resume
is
18:30 sharp.
okay, yeah, and there is a question. I'm happy to answer the question. Uh, and yes. Okay, so what makes a data set too small for neural networks, ML? Let's say I have 5 columns, including the target feature, and 25 rows. Uh, okay, so it's a question that that doesn't have answer because it definitely make it small for the neural networks because neural network have a 100,000 of parameters, so it could be 400, 500 parameters. Yeah. So and if I have a 400 parameters and I need to fit how many 25 rows, so 25 input numbers, yes. So you keep 5 for test, 20 for the input, and you have four columns and plus target variable. Yes, so it's a 4 by 20. It's 80 numbers. I need to hide 80 numbers in 400 numbers. I can easily do it. But the problem is that I will definitely overfit. That's why, if you have such a very small problem, but it's a problem which have a hope for the generalization, the old ways, which I told you, not neural network ways yet, like to build a decision tree. But again, you need to be careful if you don't have that much data. You need to have a decision tree with not too many layers. Otherwise, it will be one last leaf for one point and you definitely overfit. So is data augmentation advisable when you have a clinical data in a tabular format? Okay, so that's a difficult one because what people do if they have, for example, clinical, I mean, you can do a kind of data augmentation, but essentially what are you doing in that case? You are trying, if you have a clinical data in the tabular format, you are trying to construct a probability distribution which describe this data in the wide sense, in the sense like, what would be the typical representative of this class so that, and you can sample from that probability distribution. But it's a little bit more difficult than the tweaking image left or right. So kind of like the naive data augmentation, as I've shown you, it's very nice for the image data or something like that. But it's if you have the tabular data, which is have some of this kind, what people usually do, they try to build up, a probability distribution, which doesn't need to be super picked as a solution of the machine learning problem, but this is just, a wide distribution which describe well enough the data, and you hope that the more data which you need fall within the same probability distribution. But this is of course hope because there is no mathematical guarantees. You can do it, you can try it, and afterwards you get some additional data from real world and see are you right or not? And if you're not, you're applying some other hypothesis. Okay.
Are we all ready to resume?
I assume so.
Yes, we can begin.
Okay, good. So we can continue. Let me quickly finish with the rough run for the what is the structure in the images, because, okay, so, and afterwards we'll come to the practical part of the things. But the notebooks should be in the Canvas and also in the Slack. Okay. So from the point of view of the computer, essentially image is just a 2D array. If it's a black and white image, is a 2D array with just intensities of each pixel, and the color image is the 2D arrays, essentially, with the intensities of the red, green, and blue, or any other ways of representing color which one can use. Okay? So we have this issue that obviously images have this issue of the in structure of the translation invariance, yes, so that if we take an image and if we shift it a little bit, we can get the image essentially is the same, but of course on some stage there will be a point when a lot of information is removed. So because here we all could say that it's still 3, but on this image we can already start wondering maybe it's 8 or maybe this is 8 and so on. Okay, or on the other note, if we have, and sometimes this invariance with respect to the shifts called translation equivariance, so that if you do the object tracking, if you shift it, hold the image a little bit, your object will be shifted, or kind of the tracking of the object will be shifted in the same way. Okay, so what basic operation, or what is the crucial difference between your vanilla neural network and this convolutional neural network is? And the convolutional is the name. And what is a convolution? Convolution is an operation where you take all of these bunch of pixels and what this image is not kind of, and you make a correspondence of 1 pixel on the next level. But the way you do it with the help of the extra thing, which is called filter. And that's filters that they exactly getting trained during the training process. So it's not just you take something like an average or something like that and make it corresponding to the one picture. You do the transformation. And the transformation is depends on the convolution mask. And those masks are getting trained, or filters are getting trained. So just an average or just taking the maximum is called pooling layers, and that's also they exist, so that you take 4 pixels and you take a maximum. So this is one, or it's called, this kind of operation is called max pool or max pooling layer, or you can also, for example, calculate an average. Okay, so what is convolutional filters and how they look like? For example, you have a filter which is looking like this. And so what do? You essentially multiply, yeah, every information, kind of like, you apply it, and the filter is smaller than an image, like here, because filter here will be also 3 by 3, and you multiply each item in the filter on each item on the pixel, and adapt in the corresponding way. So you get a smaller image where you applied filter. And just looking at this, it seems like a little bit useless or senseless exercise, but I think there will be just now a few filters which can make it an epsilon more clear why filters could be a very useful idea, or why these convolutional filters could be a very useful idea if we want to learn something about images. So we have an input to the input X, so our image, yeah. So, and we have a kernel, which not necessarily need to be rectangular or square. It could be rectangular. So, and the convolution is just defined something like this. Okay. And the typical examples, of the traditional kernels or these filters are looking like this. So you have, if you have a filter like this, it's supposed to detect horizontal line. Filter like this, supposed to detect a vertical line in the image. Filter like this will detect the 45-degree lines filter like that would detect, 45 otherwise in the other direction degree lines. And the result of application of this filter to this image, you apply it to every 3 pixels and you go through it, will result in the image like this. So what do you see? You literally see only horizontal lines. And what the training of the neural networks or convolutional neural networks do, it's outsource the design of these filters to the training algorithm. It's the what particular train do we need for this particular problem of recognition, recognize horizontal lines or not? We don't know. But the data would tell us. And the data will also tell us what kind of filters or what should be the values of the filters which we are going to get. So, and essentially this and I mentioned to you that in the past, that was the job. People were inventing these filters. People were inventing filters, to detect corners, filters to detect, for example, eyes, or filters to detect noses of the images and things like that. So, obviously, if you have a good filter which is supposed to detect nose or eye, when it's applied to this image, it's supposed not to give it just a black image without anything. Yeah. So, and think like that. Okay. Yeah, these kernels, filters, or convolutions, essentially, it's all synonyms. They were handcrafted and they were called edge detectors. In convolutional neural networks, they just learn in the training process. Because essentially what it is, it's when you want to learn some filter, for example, you want to learn the filter which goes from here into here, you need to supply a lot of images, yeah, and in that case that thing is going to have in your training algorithm only 9 parameters, yeah, or only 16 parameters if you try 4x4 filter or 3x3 filter and so on, and in the process of training it's going to recognize that it should be something like that. Okay, so yes, and the entries of the filters are learnable parameters. And for example, this is the example of how the filter is applied to this image. And that's the values of the entries and the filter, these small letters, and they will produce to you from this set of numbers, this set of numbers. Okay? Convolutional. So there are some typical parameters which you need to deal with if you apply, I don't know, convolutional filters as we're going to see now in TensorFlow. So we have a filter, for example, 2x2. We have a stride on this side, stride on this side. And the output dimension is the input dimension divided by the stride dimension. And now with the strides, you get an extra thing. So you can apply filter, and you see here how it's applied. It's padded, and this is called exactly padding. So it's added zeros outside. The image is this one. Your information is where it is, 1005. But here it's added extra layer of zeros, and this is optional. So you can do it or you can skip it. And when you move along the X and along the Y axis, you can do it with a step of 1. So you go this 4, and afterwards this 4, and afterwards this 4, and so on. Or you can do this 1, and afterwards this 1, and afterwards this 1, and so on. So this is the parameters or hyperparameters, to be more precise, which you can control in your algorithm. And as a function of that, you are going to get, a different training, different results, but, you need to try and see what works. Okay, so yes, and that's what's called padding, this adding extra layer of zeros, and you can add it or not add it as a function of how you like it. So stride 1, 0 padding 1. So it's mean that step of 1 and 0 padding is only one line of zeros, because here we have a filter 3x3, so we might have a two layers of zeros. Okay. For example, this is example of stride 2. So it's mean that step 2, and the stride is here, right? Stride 2, which means, if it don't specify, it's mean that it's a stride 2 along the X and Y axis, because in principle, you can have a different speed along the X axis and different speed along the Y axis if we're going to talk about the 2D images. So stride 2 means that, we have a shift of 2, and the 0 padding 1, it means that we added one layer of zeros around our input image information. Okay? Okay, so that's a technical question, not to me. Okay. So convolutional layers, they have a bunch of hyperparameters. So you can choose the filter size or kernel size. You can choose the stride. You can choose how much of zero padding you like, and you can choose essentially how many filters are you going to have, because you could have more than one filter. So you could have, this filter, that filter, and so on. And what you're going to see now on the illustrations of this neural network architectures, that you have quite a few filters. Yeah. Together, these determine the relationship between the input tensor, input multidimensional metrics, and the output tensor, output multidimensional metrics. Okay, so and that's how it's usually drawn. So you have an input layer, so you have a filter, you have a stride size, and it's mapping a number of filters they create width. So you reduce the width like this by applying the filters, but you increase the length of the, so to say, of the number of layers. Okay, so and there is a few more examples of applying of the filters and for the different sizes. So kernel size 3, yeah. Stride 2 means step 2, and padding 1, it's mean that the extra layer of zeros. Here is again, we have 3 input channels, so the kernel size will be 3 by 3 by 3. So it's a little bit more difficult to imagine, but if it's a colored image, that is your input channels. 2 output channels, and you can calculate also the total number of parameters. And if you are serious and very interested in learning how to do computer vision, you can write down, and it's on the slides, this website, CS231. It's a very famous course in one of the Ivy League universities, and they have all their materials online. And over there you need to write your convolutional neural network essentially from scratch. And I think stage they now switch to Python as well, but on some stage you were supposed to do it in Java. Okay, so pooling layers. So pooling layers, the typical is the max pooling. So it just, you take corresponding groups of pixels and find the maximum intensity, and you replace it with one pixel with corresponding intensity. And that's all. So you go through the image and you replace it with a corresponding maximum value. Okay? So for the pooling layers, what parameters or hyperparameters we have? We have kernel size. Again, what is the pooling size? Is it 2 by 2? Is it 3 by 3? Is it 4 by 4? Is it 4 by 5? And so on. Stride, how you shift. Amount of zero padding if you want it. And why you might want the zero padding if you take a maximum value, because anyway, it's not going to affect the result, yeah? But why you want the zero padding if you want to control the output size, yeah? And the pooling function, because as I mentioned to you, if it's max, the zero padding doesn't change anything. But if it's average, for example, but usually it's a max, and the layer is called max pool. Yes, kind of in that case, of course, if you have a zero padding, the pooling for the average, for example, will be affected by the extra zeros. Yes, and unlike convolution, pooling layers separate on the channel separately, so an input channel and output channels. Okay, so and this is essentially 2 very basic layers for the convolutional neural networks, convolution and pooling. Convolutional layers are translation equivariant, means that you apply one and the same filter to the each bit, and so if you shift the picture, it's of course doesn't change. So if object is translated, convolution output translated in the same amount, and produce image shape features which retain association with the input pixels. And this is also a very interesting thing, because besides kind of the hidden behind all of these words, there is a problem that it's very interesting to understand what the neural networks are learning, because they have so many parameters. And with the image network, you can really see how all these kernels, which people were handcrafted manually, now they design automatically. And for example, if it's a data set which recognize, I don't know, cars or types of cars or whatever, so you will see that in the individual layers, it's really it's a certain bunches of kernels which are learning a particular feature of the certain types of the cars. all kind of like, I don't know, of the cats or dogs or whatever. So this is quite interesting from that perspective. Pooling layers, their translation invariant, their binning to make the output insensitive to translation also reduces dimensionality. Yes, and they're both combined in the modern architectures. Okay, so now this is the first serious and fancy example of the architecture which I mentioned to you. That's one which create a breakthrough in the computer vision, essentially, which beats the ImageNet competition, the previous result by, I think, something like 10%. So it was looking like this. So it's have 11 by 11 convolutions, 96 kernels. Yeah, and so it was kind of like this, and afterwards 5 by 5 convolutions, 3 by 3 convolutions, 3 by 3 convolutions, and this is a number of filters, yeah, 3 by 3 convolutions and corresponding pooling, yeah, and afterwards it's end up with a fully connected layer, another fully connected layer, so like a standard neural network, and afterwards final fully connected layer, which have 1,000 outputs because there is 1,000 classes. And of course here, after this 1,000 layers, output means that you afterwards sit on top of the softmax so that you get instead of whatever numbers, you get a list of probabilities. And each of these contains of convolution, kernel size 11, so 11 by 11, stride 4, 96 output channels. So you are designing automatically 11 by 11 different kernels, and there are 96 of them. Yeah, so you don't design them, you do them during the training. Afterwards, there was a relo activation. Afterwards, there was a pooling with a kernel size 3, stride 2, no padding. And afterwards, batch normalization, local normalization of the layers, so prevent the variance drift. So, and that was repeated through the several iterations. Yeah, so usually it's also could be written like this. So input images in the ImageNet are 227 by 227 by 3 because it's colored images. Yeah, afterwards you get the convolutions, as I mentioned to you. So when you create, instead of 227 by 227, you get 55 by 55, but now it's instead of 3, it's 96 width. Now you do pooling, so it's reducing the dimension to 27, 27, but the number of layers is, or kind of this number of output channels is 96. Now you do another convolution, 5 by 5 with padding 2, but now you have 256 kernels. So as a result, what you get a bunch of images or whatever. It's already, okay, formally it's still images. Yes, 27 by 27, but now it's 257. So it's extended even more wider. And now you do another convolution. Yeah. And afterwards you do one more convolution, and you make it smaller and smaller, but longer and longer, but without padding and without, so you maintain the dimension 13 by 13. And afterwards, finally, you shove it down towards the fully connected layer. So this is a standard neural network, like dense neural network, as we've seen before. Yeah, so for 96 or 4,000 neurons, another 4,000 neurons fully connected. It means that each connected to everyone. And afterwards to the 1,000 neurons and the softmax, so that the output is the probabilities. And I think it took them quite a while to train it. So I think, if I'm not mistaken, something like a week to train that neural network, which on that instance it was unthinkable. Now it's peanuts for this kind of tasks, and they managed to beat whatever was the record by far. Okay, so and this is a very nice graph of how yes, and now we can see exactly how. So on the corresponding competition, what we have a 28% error was, and afterwards 25, and afterwards from 25.8 to 16.4. So this was the jump of AlexNet in 2012. Next year, it was decreased even more by 5% error and it was an 8-layer neural network, convolutional neural network. Afterwards, it's a very famous and standard neural network which is called VGG. So that was already 19 layers. GoogleNet next year was 22 layers. And essentially after all of that stopped, that was ResNet, which dropped down to the 4% or below 4%, but it's have 152 layers, which was unthinkable at that instant. Okay, so, and that's essentially everything which I wanted to tell you in theory about convolutional neural networks. And I don't know, do we have any questions? And if not, we can go to the practical side of the story. Okay, so let's jump into the practical side of the story. I assume that you all have notebooks, yeah? Because they are in the Slack, but they're also in Canvas, whatever is available. So let me stop sharing and let me switch to Okay. So I suggest that we do quickly the notebook, not about neural network first, but about the PCA and clustering. But the clustering part we already seen, but we can do PCA. I think it's a nice bit because it's also how to apply PCA and afterwards how to apply TSNE. And afterwards, because we're going to be here, introduce the data set which we've seen, which we are going to see again. And afterwards, we can switch to the games with the neural networks. Okay. And also I upload the notebook about the support vector machine classification. Okay, let's see what will be with, should we start with that one? Okay, now let's start with, because there was a question, and there was the question about the medical data, yeah? Yeah, because I was also thinking now that you're asking Lisa that is the data augmentation is advisable? I mean, I answered your question what you need to do if you do the data augmentation, but the obvious answer is if you have enough data for the old style machine learning techniques like forests or this kind of thing, so or even just decision trees, maybe you don't want to do any data augmentation because the main problem of the neural networks is that you cannot explain what they do. There is a separate direction in the modern machine learning is explainability. So try to understand why neural network decided this is a cat or this is a dog. And in the question, this is a cat and this is a dog is not too bad. It's much more difficult when you have a lot of historical data of the court trials, and afterwards you use the AI advisor to decide on the sentences of people, and it's very difficult to say that this person should be sent to jail for the 10 years. Why? Just because neural network decides so. It's a very, let's put it mildly, unethical way of using the technology. So, and from this perspective, if one is claiming that you need to at least to be able to give some story why neural network, on which reasons neural network have decided that the sentence should be this or sentence should be that, or you should grant bail or you shouldn't grant bail to the person, or if it's why the neural network is thinking that somebody have a certain type of disease and now needs to undergo, for example, even excessive screening, or could be very, first of all, expensive, and secondly, it could be very unpleasant if it's some sort of a screening which relate to, I don't know, taking to the bone marrow and things like that, for example. So using the things like decision trees or other techniques like that, you can really have an explainable structure, because if you're going to say, okay, this parameter is greater than this or or I don't know, tumor size is greater than that or not greater. Okay, if the tumor size is large enough, okay, so this, and this is also sounds a little bit logical with whatever is the, so, and afterwards, oh, this tumor have these things or that things on surface or things like that, or is the inside, what is the density and things like this. So if you can build a tree of the decisions, you can use this tree of the decision on classification problem. Is a tumor good or not good, or should be treated immediately, or one can wait and observe. You can take this information to the medical professional. For example, if we're talking about the tumors, we're talking about things like cancer. So you can take to the cancer expert or surgeon and so on and so forth, and ask them, okay, so that's what we have. Can we make sense of it, or is it just an artifact of the data? And if you can do explainable thing, you can do it. And if you cannot do explainable thing, if it's just oh, just spit out numbers, nobody can tell you what it is, and it will be very difficult to convince anybody that this this result of application of artificial intelligence or machine learning towards the medical data have a potential essentially. Okay, but now let's go to okay, first let's go. Okay, so let's go to the Firefox, and we were doing this one, yeah. When do I have it opened already? Yes, I have it opened already. Let's close it. Okay, so let's go back very quickly because we have already this notebook because of k-means clustering, and I'm not going to run again through the theory of the PCA. Let's just see how it's implemented. So when it's going to be implemented using the very vanilla so-called a standard data set, which is called iris data set, which is a very standard data set. And as you see, it's even part of the scikit-learn because in the scikit-learn, there is some very standard data sets. And the iris data set, if you don't know, it's a data set which contains the parameters of the three type of irises, which is the flower. And based on that, you need to decide what kind of type of iris is this given flower. Okay, so it's using some representation to show there is a three parameter: sepal length, sepal width, and something else. Yes, and the petal length. Yeah, and that's a distribution of the points. So and what we wanted to do, we wanted to project it on 2D and see how so we say, okay, do we need all three input features? And we want to use the PCA to see can we reduce it. So what we're going to do, first of all, we're going to split the data set into the training and test. In this step, you already seen. Second, we wanted to see what will be the default prediction. Yeah, so kind of like if we use some decision tree classifier and we just apply it and see what's happening. Yeah, so let's do it. So without any PCA. So and we're getting okay. Good enough accuracy, to be honest, out of the box. But now let's do the PCA and see how PCA fits into this story. So we're going to do PCA, which is a part of decompositions, where the decompositions, okay, so they should be loaded somewhere here, yes. Scikit-learn decompositions. So, and if you're curious what other decompositions are available, you just go scikit-learn.decomposition. And Python should show you the list. Okay. Okay, so where we are here. Yes, so we're saying that out of PCA, we're interested only in two components because, of course, the features are three-dimensional. So if we don't specify number of components, it's going to give us all components and there will be three components. Yeah. And now we're interested only in two and we can plot these two components. And let's see how it looks like. And you see kind of the projection of this world, three-dimensional image, into the components which maximally explain variance on 2D, lead us this picture. And it's in some sense, it's a partial success because what one could see immediately, so that using this projection, we can definitely separate this type of irises from these two type of irises. Yes, from this setosa, you can say that, okay, along this component, if the parameter is smaller than whatever the minus 1.5, you're definitely in this class. While here it's a little bit more difficult because you cannot draw simple straight line, but you can also imagine the drawing boundary somewhere here, so that it will work not bad, maybe not perfect, but not bad. Okay, so now let's try to use this information of kind of like what we're now trying to do and trying to use this PCA as a feature in order to do our supervision. So X train, X test, Y train, Y test, training split, but now we're applying it to the X's which are coming from PCA. Okay, so from PCA we get our, instead of three component features, we get a two component features, and that will be our new, so to say, our new two features. Yeah, and we're doing absolutely the same thing. We're doing decision tree classifier, X train, Y train. And yeah, if it works, yes, we're getting a little bit better accuracy, 91% instead of 88 or 89%. So you see, kind of even in here, it's clear, but so that is work, and it could be a very useful thing to do. At least that's an option which you need to keep under consideration. Okay. So what else do we have in this nice notebook? Okay, so we can also calculate, no, now it's an interesting bit. So because now we can calculate the accuracy. Yes, because then, yeah, accuracy does not increase significantly, but increased a little bit. Yeah, but if you have many kind of the larger data set, but what you can also do, and many people do it in practice, you can not, because what we have done, we take these three features and we convert it into two features and apply only these two features as the new training data set. But what you can do, you can add these two features to your three features existing. And that's what is very often happens in the different machine learning tasks, because this is just an extra information. Yes, and now what we wanted to see, so we want to see that the first component of PCA explain 92% of the variance. Yeah, and the second component of PCA explain 5% of the variance. Essentially, what does it mean? But I mean, this is in some sense, it's more or less clear, because the first component is probably this one, yeah? Plot, yes. Yeah. Yeah, so kind of like it's clear that this line cuts out immediately this class, and line somewhere here immediately kind of separate these classes with the error, of course. But you can imagine that only by going along this axis, you can do a pretty good classification of these flowers. Yeah. Okay, now we're going to a little bit more interesting data set, and the data set where the PCA will fail, and we've seen it already fail in the lectures. So we're going to do the digits data sets. So it's a digits, but it's a in here in scikit-learn, it's a smaller data set of the digit data set, because it's only 1,800 entries, while in MNIST in the TensorFlow and the Keras is, I think, 60,000 images or something like that. Okay, so because this we can see from the shape, yes, and they're also 8 by 8 images. 64. What is 64? It's 8 by 8 squares. While I think the one which is in TensorFlow, it's higher resolution. I think it's 28 by 28. Okay, so and we can see how they look like. It's a bunch of numbers, but now we can represent these numbers in a little bit nicer way. So that's how they look like, and you can try to distinguish, yes, because this is obviously 0, this is 1, this is, I don't know, is it 4? This looks like 3, and so on. But the other data set will be much more explicit. Okay, but even this one, it's only 64 components, dimensions, or features, and now we want to reduce it to 2 using PCA, and wanted to plot it. And it's a 2-dimensional projection of that data set, and the different colors means different classes. And you see it's all over the place. Essentially, 2 components do not explain anything, or do not explain much. So because there is no way that you can say what's the difference between 5 and 4. Okay, maybe 5 and, because this is 5s and 4s are here. Okay, maybe this is 5s and these are 4s, yeah. So, but it's still very difficult to do the classification task using only this 2-dimensional projection, which is linear. But what is very, very interesting, what we are going to see now, so that if we go to the nonlinear projection, which is called TSNE, and there are several others, we could be lucky. And in that case, yeah, we could explain. So, and okay, in scikit-learn, TSNE is the natural part, and the TSNE is the stochastic nonlinear embedding. And we can do that. And it will take a little bit more time. Yeah, because you see it's take 11 seconds. But what we could see using nonlinear projection technique, all the information which is contained in those 64 by 64 blocks or 8 by 8 blocks, 64 features, could be compressed down using some nonlinear transformation to the 2 features only, yeah? Because it's clear that we can quite safely, with a very high probability, this is some sort of outliers, but if you're sitting in this part of the corner, you are 0. If you're sitting here, you are very likely 6. Yes, there is again one outlier. So it wouldn't be a perfect classification, but it will be classification with a very high accuracy, because if we now apply that transformation and give this to the classifier will be able to draw enough decision boundaries so that when we give a new input, pass it through the TSNA transformation so that we would be able to get it. So, if PCA doesn't work for your data nicely, try some other functions which might work nicely. Okay. And now there is one more interesting bit. So in fact, we see that, here we can nicely explain, but what's, the question is, the question was, when do we want to stop with PCA? How many features of PCA we need to take? Here we take two-dimensional features because, it's just nicely, you can show the two-dimensional graph. You can maybe go for three-dimensional in the three-dimensional graph, but, more features, it's difficult to decide. And what you can take, you can try to say how much of variance it could explain, how many features you need to take to explain variance. And for example, yeah, kind of like here, there is an example that we take up to the 21 principal components of your 64 components, because it will be 64 one of the PCA for this handwritten digits. And again, we do PCA decomposition fit. And now what we are plotting PCA explain variance ratio as a function of number of components. And as you see, we get, this is our ratio kind of, and as you see, the first components, they explain nicely. And now the question is like, we can explain 90% of the variance with, roughly speaking, 20 components. And this could be a useful thing because again, you need to tell, as the person who is applying machine learning model for something, how much you're happy to tolerate as a noise, how much is enough. So if you want everything, yes, you need to go all the way through, but you might just not have enough compute to go all the way through. So and plots like this allows you to say that, okay, so I'm happy with the 90% of the variance. Where should I stop? Okay. Okay, and the clustering, I think we have a little bit of clustering already. I don't think that we need to play this game again. You're welcome to try it. Are there any questions on dimensionality reduction? I'm not sure that Lisa understood the question. So, does the nonlinear projection affect interpretation of the results? In regression, using nonlinear approach applied to the data that was not normally distributed requires interpretation of the results in a different way for the result of the linear regression. Okay. So you need to distinguish two things. Your input normalization of the data. I mean, the reason that why yesterday I mentioned that we have a problem with interpretation of the results of the training is because if your features are on a different scale, you cannot make a statements about the coefficients which are telling you importance of these features. Because if you compare a number 1,000 to a number 1 to make them on the same scale, number 1 needs to be multiplied by 1,000 and 1,000 need to be multiplied by 1. So, and that's why I just make it difficult to compare. So that's why you need to standardize your features, especially if they're all the way around from the beginning. Okay, so nonlinearity does not affect the interpretability, because what is nonlinearity is doing to us, it just doing the feature mapping, but this space where you map features is just a nonlinear space. It's just nonlinear transformation, like when you do the x squared. Does it affect interpretability? For example, if you do a linear regression to the data and you find that linear regression do not work, and you need to add, for example, quadratic and the cubic features. It's help your interpretability in which sense? In the sense, for example, you will find that, for example, if you're going to plot, let's take something very simple and silly, yes? So let's say that I have a bunch of balls, yeah, or kind of the empty balls, and I can fill it with water, and I'm going to plot the relationship between and the balls don't need to be perfectly circular, and I need to explain the relationship between the maximum linear size of the ball and the volume. Yes, and it clearly should go cubically, yeah, or roughly speaking, cubically. But if I plot it on the graph, I will get a point, and if I will try to fit it with linear relations, I will not get anything. And when I see that, okay, the best result is cubic, in that case, I can make a statement. What is the generic relationship between the volume of the body and its linear sizes? It's not affecting my interpretability. It's assisting my interpretability. And in the same way, I mean, with these nonlinear embeddings, because they're not so straightforward, it's maybe will be difficult to write explicit function, but it's just telling you that there is a nonlinear transformation which can make the data which was linearly separable. Yeah, because what does it mean that we see this? It means that we can literally draw a boundary between these points and say that everybody who is falling inside of this boundary is also a blue guy, or everybody who is falling inside of this uh, light blue boundary, or whatever the color is also belonging to the same class. So the same with the red ones. So we're turning this non-linearly separable because we try to do the linear transformation, and it's clearly we cannot separate it with the clear boundaries. Non-linearly separable data set into the linearly separable data set. What does the point of intersection means on the last graph? On the last graph, the point of intersection is just to indicate to you so that if we're happy with explainability of the 90% of the variance of the data, how many components we need to take. So this is a 90% of the variance of the data, and it crosses somewhere here, or approximately here, and we can, if we go down, we can see how many components of the PCA we need to take. So the line doesn't have any significance. So if you want 95% of the variance, you need to put the red line going here, and your cross will be somewhere down here. Or if you're happy with the 80% of the data, you can stick to the smaller number of PCA points. Okay? The CNN images weren't sharp with the reduction of dimensionality from 64 to 2 improve the images. Can the improvement be visualized in a pixel? I'm not sure that I fully understand this. First of all, CNN images here, they're not CNN images. This is just an images of the data set. We're going to get a little bit more sharper images in this CNN, but you know what you need to remember always, you need to always pixelize your image. So you need to, whatever image you have, and you need to tell, you know, how much resolution you are prepared to tolerate on the image. And what is the problem? Of course, you want the higher resolution than you can, but the problem is the higher resolution is the more numbers you're going to have in your input matrix. And it's mean that the more memory you need to have, the slower the matrix multiplication is going to happen. So you need to maintain the balance between so that, you know, we can still recognize that this looks like 0 and this looks like 1. So we can formulate it as a problem. And with the 64 features, so 64 input numbers, because it's 8 by 8, we can still solve it relatively fast. If I do it ultra high resolution, and it will be, you know, 100 by 100 pixels, in that case, it could look very nice. Although 100 by 100 pixels could be also not so nice, but you know, it will be much better. But it means that I have my input vector, instead of being 64 numbers, is it 10,000 numbers. And now, because every number, in order to store every number as a function, what kind of number it is it integer, is it real, is it non-real, and so on, or whatever the float 64, or whatever, there's amount of memory which you need to have. And can you fit this matrix, for example, on the graphic card, so in your memory for multiplication? And that's a question. I mean, by doing this reduction of dimensionality, we're not improving images at all. Images are where they were. You know, when you're talking about the improving of the images, there are neural networks or convolutional neural networks which are trained to improve the resolution of the images. But in that case, you have an input, I don't know, 20 by 20 or 100 by 100, and it can give you out 1,000 by 1,000. But whatever the algorithm is putting in between, it's a separate story. And usually, these kind of algorithms, they work similar to the networks which are called autoencoder networks. Is there a reason why plot for selecting components here goes upwards compared to the other elbow plots that are descending? I'm not sure what are the elbow plots. What do you mean? You mean where we're plotting the components? So here's going upwards because it's a cumulative it's a cumulative explainability ratio. So it means that first component, for example, can explain to you 10%. When we're going here from 1 to 2, we're getting how much first component can explain and the second component can explain. That's why it's naturally increasing and increasing from 0 to 100%. That's why it's supposed to grow, because every component explains a little bit. And we're always adding a small number, and that's why it's going up. On the other graph, which we had, uh, okay, it was where it was in the lecture. It was the plot of how much variance one component explained, not the sum, but one. That how much variance first component is explained, how much variance second component is explained, how much variance third component is explained. In order to turn that graph into this graph, we will have to add in the variance which is explained by this corresponding component, and in that case, you would also get an increased graph. Does it make sense? So it's slightly different graphs, they contain a slightly different information. And it's just a function of how much, and you might want to use both graphs because, again, the first graph, or you can also interpret the first graph as you can, in the same way, plot not the how much of variance it can explain, but you can just plot these eigenvalues, because the eigenvalues essentially is given how much variance they will be essentially proportional. So, and you can plot the spectrum of the covariance matrix, and in that case, so list of eigenvalue in the decreasing order, you'll see and how quickly eigenvalues are falling down. It's really telling you where you need to cut things. And this is a very typical approach for the data compression in many, many numerical domains. For example, in condensed metaphysics, there are objects which are called tensor networks or matrix product state, where it's the same idea of how you can simulate a very difficult things or very computationally intensive things. So essentially, you diagonalize thing, you get an eigenvalues, and you throw away the small ones. And in that case, you really want that your eigenvalues fall very quickly, or in this case, your variance explainability is falling very quickly as which component it is, and it works very nicely. Okay. Can this PCA and N be applied to a security field resolving crime, especially where the suspect is far away from CCTV? Okay, so we haven't yet done neural networks and PCA, if the suspects are far away, if the information is not there, you cannot invent the information. That's another thing which one need to know. If one wants to use neural networks and think like this for the crime prevention, there are the systems like that exist, and they're employed already worldwide in the several large cities, and that's why in the cities, for example, with my background, I can tell you, like in a city like Moscow, there is no petty crime. Why there is no petty crime? Because there is enough cameras. They don't have a superb resolution, but there is enough camera coverage so that you could be tracked. So, if somebody kind of steal my wallet, that person could be tracked and nobody will run after you. They just, next morning, the policeman will knock your door and say, "Good morning. I think you're hiding something from us." And, that's why these kind of events are not happening. And such system exists already in the several large cities all over the world. So if you have a camera coverage, you don't need to have a super resolution, because using the object detection and tracking, you can just track people. And this works. This works fine. But you need the coverage, and you need, of course, you need the center of the processing of this information. Okay, so let's very briefly go for the notebook number 3 about the support vector machine classification, and partially because it's also related to the medical data, to the kind of vanilla medical data or standard medical data, which is this. There is a standard um, breast cancer data set, which people analyze left, right, and center, and so you can also use it for training, but for our purposes, it's just a problem for the classification. So what do we need here? Again, we use here standard packages, pandas, numpy, matplotlib, seaborn for drawing, yes, and again, and you see it's a so standard data set so that it's a part of the scikit-learn. So we need to load data set. So there are some keys or features of the data set, yes. So data, target, frame, target names, description, feature names, file name, and data module. So description is giving us what exactly is the data set. Yeah, because the fact that we're addressing cancer.keys means what? That this is a dictionary, yeah? So we need to have the dictionary which have a keys data that will contain data. Target is that what we want to predict, but also have some additional things, for example, description. So if we wanted to know what are the features, so there is a description of the features, and there is a description of the data set, and also have a bibliographical references so that if you want to use it, for example, to benchmark your particular machine learning algorithm, you shouldn't cite scikit-learn, you should cite the original research of the people who have collected and curated this data set. Okay, so we can check the feature names. And now we can load the data. So again, cancer as a dictionary, we're addressing it with the dictionary key data. And the columns names are the feature names, and we are getting the data set. So we have 569 entries. So it have some characteristics, each feature. Okay. So one can check, do we have any missing data? And we don't have a missing data because, of course, as it's expected, because it's a curated data set. But that's the thing which one needs to be prepared to work with. If you're working with real, for example, medical data, which is coming, I don't know, from the hospital, and they want you to sign, I don't know, certain agreements about anonymizing of the data and things like that, one should be prepared that the data will be not a high quality data, and you will need to tweak a lot with the reality, because in reality, people are not typing the data perfectly. People are typing data as it goes, and there will be errors, there will be missing data, and that's you also need to think what you need to do with that. Okay, so we can check how the targets are looking like, or what we want to predict. So it's a zeros and ones, yes, no. Okay, so we can add it to our data just for the analysis purposes. So now we can do what is called and this is a very typical thing, what is called the exploratory data analysis. So we can just see what are we dealing with, and what we see that of the what we need to predict, we have 200 and something entries with the class 0, and just above 350 entries with the class 1. Okay, so my notebook will be a little bit unhappy, but we are going to still run it so we can do the box plots and see how it looks like. Okay, so there'll be a bunch of warning, but afterwards we're going to see what is the correlations, or kind of how the uh, having or not having cancer is related to each feature, like mean radius and so on and so forth. And by the way, what is the meaning of the box plot? What is the width here? What is the width here? What are the circles? Okay, that sounds not bad. Yes. Q1, median, and Q3. Okay, okay, okay. And who are these guys? And who are the dots? Boxplot give a 5-number summary and outliers. Okay. Yeah. I mean, the dots are outliers. And yes. Okay. Q1, Q3, median, and so on. Okay. And we can see, how the statistics is related to our variable which we want to predict, and what we could definitely see, so that the most of the features, they have some relation. So kind of like, just by looking at here and here, you could see that these are not overlapping box plots completely, so they are shifted with respect to each other. So we should be able, so there is a relationship. So kind of like mean area have something to do. So using mean area, there is a correlation between having cancer, not having cancer, for example, and so on and so forth. But also there is interesting that some of the features have quite a few outliers and some not. Okay. Yes, you see, not all features separate out the cancer prediction equally, certainly. Yes, and we can, for example, to see, mean area vs cancer, and what else? The mean smoothness vs cancer. So we have here the distribution of the mean. So this is a mean area vs cancer and mean smoothness vs cancer. So we have overlaps. So it means that it's not a perfect separation, but we can already build some separation. Okay. So now again, now let's go to the training. So what do we need to do? We need, first of all, for the features, we need to take away cancer, because that's a variable which we want to predict. Yeah, so checking that we are fine. Yes, that the last column is a useful feature. Now this becomes our target. Yeah, and yes, it's our target. We could see it. Yeah, now we do the test, train, and split, which we already seen a million times. Yeah, test, train, train, test, y, and the same for the y's. Uh, haven't I not loaded it? Where is my scikit-learn? Where are you? Why? Because I didn't run these things. Sorry. Yes, immediate. Okay, good. Okay, so we've done the split. And now we're going to apply, out of the box classifier, which is called support vector classifier. Again, with the scikit-learn, it's all straightforward. We create model, we fit model. And now we do the predictions. Okay, so we can grab the confusion matrix because it's a binary classification, we can see that how the confusion matrix is looking like. So we have a true positive, true negative, and we have a false positive and false negative, so that we see that out of the box, it doesn't work too bad. But I don't think that I'm going to run it, but let's just quickly run it through. So because support vector classifier with a simple feature transform, because support vector machines is the special form of the machine learning models, which could have built-in features, feature transformations, and they are and essentially the typical this feature transformation, when it's linear, it's just a linear classifier similar to the linear regression, but for the linear classification tasks. You can have a polynomial feature space, or you can have it's called RFB, it's radial base function. It's a difference between the entries. It's a distance like e to the minus x squared, where the x is a distance between the instances. And we can run in a grid search for the different parameters of the support vector machine. And for the kernel is exactly this radial base functions. And you can run it and you'll find some values, and afterwards you can check again how the confusion matrix is looking like, and you'll see that it looks a little bit better because there is a less of diagonal elements. And you can do it again, and you can play this game of optimization. Okay, so I just want to give you this very quick example. And the beauty of this is that after, if we can produce a nice machine learning pipeline and we can produce the results because it's support vector machine with well-defined kernel and so on. We could really interpret the data. We can try to think why we're getting the result as we're getting it. Okay, so now let's jump into the world of neural networks. Okay, yes, okay. So what are we going to do here? We are going to play with the MNIST dataset, and what you're going to see that MNIST dataset, which is coming as a part of the TensorFlow, is much larger. And also you can always check how the data set is looking like. So we can go to the trained data and see what are we dealing with. So that's how the input image is looking like. We're now also going to see it as an image, but also we can also check, for example, shape. So it's a 28 by 28. You remember that in the previous notebook, we have a 8 by 8 images, but this one are going to be already 28 by 28. It means that there will be more features, but it will be much more nicely looking like, okay? So, and automatically in the structure of this trained data, test data, it's loading it automatically, and it's loading it as in the structure of these tuples where it's have images, labels, images, labels. So that's the thing which you need to check. Usually you can check it experimentally or with documentation if you use the data sets which are part of the packages, how they organize it. Okay. So now the next thing is that okay, so let's before we run that, let me show you. So, oops. So how the training data set is looking like? It's 60,000 images, 28 by 28. Yeah, and oops, no, test. Test images is 10,000. So it's 70,000 images, 60,000 in the training, 10,000 in the test. And that's already looking much more like, a data set and we have 10 classes. Yeah. So we can check what is the train labels. Yeah. So it's a 60,000, but if we do now train labels, what we can do? Describe, yeah. What it is. Labels. What is labels? What is it? Array? Okay, it's already array. Okay, we can just give a look into that. So it will be numbers from 0 to 9. Okay. Or we could do train labels. Can we do it like this? No, like this. 9. Yeah. And the thing is that train images, let's do the same thing. So the intensity here is loaded as a number from 0 to 255. And this is not so good to deal with such large integers. So that's why typically what is done, you rescale it from 0 to 1. Okay, so that's why you do the X-train images. First of all, is being because it's not what now going to do the deep neural network or dense neural network, sorry, or deep neural network, that doesn't matter here. It's not convolutional neural network. We're going to take this 28 by 28 and stream it line like into the single line. So that's why we do reshape 60,000 to 718, and afterwards we divide all the entries and we transfer it from integers into the float, into the real numbers, and divide it by 255. So that each entry, like for example, now it's like this. So now let's do this. Yeah. So now it's an array 28 by 28 with numbers. So, and we're transferring it into the vectors where numbers are going to be from 0 and these integers. and we're transforming it into the numbers from 0 to 1. Okay. Okay, so now what's happening now and what is very good and very useful, we're transferring our labels because now how our labels are looking like. Our labels is a number 0, 1, 2, 3, 4, blah, blah, blah. But we're transferring into the categorical. So instead of making it 0, 1, 2, 3, we're saying, okay, 0 class will be an array 1, 0, 0, 0, 0, and 9 zeros. Class 1 will be a vector 0, 1, 0, 0, 0, 0, and so on. So this is called the categorical transformation, and it's much easier for the training purposes. Okay, now we can check that everything is looking in a similar way. Okay, so now we can pick a random image and plot it. Yeah, so now you can see it looks much nicer. We can do it in a little bit fancier way in the grid. So that's how the data set is looking like. This is your 5, 0, 4, 9, 3, 1, and so on. And you see it's different ones, different twos, different fives, and so on. Now we need to build our neural network. And it's going to be a very, very simple and naive neural network. It's only going to have one hidden layer. Yeah. So we start with the model is the TensorFlow Keras model sequential. So we're going to build a sequential model. Next, we're going to add only one dense layer or fully connected layer, which is going to have 512 neurons. Activation reload. Input shape is 28 by 28 because that's our input shape. Yeah. And we're going to add now immediately output layer, which have 10 neurons. Why 10? Because we have 10 classes. And the activation is softmax, yeah, because we need to, it's spitting to us probabilities. Okay, so we can see the model summary. And so that these 512 neurons are having 400,000 parameters. Yeah, and this dense layer is another 5,000 parameters. Okay, so now we need to compile the model. We need to specify optimizer. And as I mentioned to you, the atom is very often used, and this is standard optimizer. Loss is going to be carried by form of entropy, because this is what is very often used for the binary classifications or for the classification task, and the multidimensional version is called categorical cross entropy. And the metric is accuracy. Okay. So now what we're going to do, and you see we're going to do only 10 epochs because, yeah, we don't want to sit here and wait for the neural network to get trained. We specify a number of epochs. We say that in each training round, we're not going to shove all 60,000 images. They're going to be shoved in the portion of 256 because this is a batch size. X train, Y train, number of epochs, batch size. And for the validation data, we're going to use the test set, which is not really entirely nice, but just for the quick one, it will work. So we can now train the neural network, and we can see that how the accuracy is increasing, and you see out of the box with a very simple network. And when we have rewritten square information with a digit as a vector, we have lost this proximity information. Kind of like we lost the fact that what makes 9 9. The fact that there is this thing and this thing, and we just turn it into the into the line. We can still achieve quite a high accuracy. Yeah, so we just do model evaluate. So instead of your model predict in the scikit-learn, here it's a model evaluate, and we can check what is the test accuracy and what is the test loss. We can get some interesting figures from our training object. Yeah, we can get a loss, validation loss, and we can plot the graph. And you see, this is our training loss, and this is our validation loss. And you see, in principle, we could keep training for longer, and we would expect to see that test loss will begin to grow while the training loss is going down. And what it will tell us that we're getting to the overfitting region within the number of epochs. because the more epochs you do, the better you describe training data. And the better you describe training data, the higher the chance that you are getting to overfitting. And you see, it's a very, very naive neural network. It doesn't have any features. There is no, where it is, yeah. There is no pooling layers. There is no normalization layers, nothing. But even out of the box, such a simple neural networks work pretty well. Okay? So, and if it wasn't working pretty well, we would need to start to play in the more fancy games. But fancy games for this particular type of data, it would be nice to do with the, if we do convolutional layers, because as I mentioned to you, kind of like what convolutional neural networks are good at, they're very good at spotting patterns and kind of local information. The fact that the several bits are typically coming together for the typical scenario of this class. So that kind of information is very nice captured by these convolutional filters. Okay. So, and we can also plot the accuracy. We getting the same thing. Yes, and that is training accuracy is going up, but also the test accuracy is going up. And as you see, it's quite high. And in principle, we could keep training it, and and you could, in principle, what could be done here out of the a little bit more fancy things. Where are you? Where are you? Yes, because if you give a look into what is the structure of the model.fit function, you will see that, for example, early stopping is sitting here as well. So we could add early stopping here. We could have said that, okay, we want 100 epochs, but we could add early stopping scenario. And in that case, it wouldn't go to the 100 epochs. It will stop after the validation laws, begin to grow within the threshold which we defined. Okay, and it's an interesting game which one could play is that, okay, we grab some, we predict some our test values, and now we grab some random index, and we can check, that the neural network is thinking that it's number one. So this is the image which we are going to recognize, and neural network is thinking that it is a number one. So, but it looks like one. I think we could buy it. So, and we can try something different. It also looks like one. It's a little bit boring. Are they all ones? No. Yeah, you see. So essentially, even in such simple scenario, it works nicely. Okay. So now we can jump to a little bit more fancy version of the same thing. It's MNIST, but using the CNN. So essentially now everything is the same, but we're not going to transform our square image into the vector. We're going to shove down the neural network, the image at the 2D array. But and for that, we're going to use convolutional neural networks. Why do the image predictions look blurred and not really clear like original images? You mean, no, I mean, they're the same blurred as, if you wanted to see with the original images, you really need to find the original image, because, this one is also looks a little bit, this 7 looks also a little bit blurred because this one looks sharp just because they're small. I think there is nothing what we do with images which is breaking them, because we're not predicting picture. We're predicting information about picture. We're not transforming the image beyond the whatever we've done with a normalization. Okay. Let's jump into the convolutional part of the story. So it's absolutely the same code in the sense like it's the same data set. Let's not see it because we just seen it just now. Same categorical transformation, same data, but now we're not, when we have done this transformation in the reshaping, we keep it 28 by 28. Okay. So here we have done push it to the 784, which is 28 multiplied by 28. Here we keep it at the same. Okay. So and we can check that, It's the same data. Oh, this is a number, and this is interesting number because it's not that obvious. Probably it's something like 5, and we can check to see the blurriness. Okay, here it was 4,000. I will have the same. Or is it shuffled or not? No. So it's the same 7. Okay. So again, one can play the same game and see the same numbers, but now we're now building the convolutional neural network. So again, sequential model. Yeah. So, but now what do? We define a convolutional layer. How the convolutional layer is working, and we specify that it's a convolution 2D because first of all, we could have a convolution in 1D, and also you can have a convolution in 3D. Because you can imagine that your information is, for example, speaking of the medical data, it could be some form of the computer tomography of the, I don't know, human brain and things like that. And in that case, it's a 3D information. Yeah. So, but you still, or it's kind of the full body scan where you can, trying to identify some medical issues. And in that case, that could be, you can use the 3D convolutions. So, and now we have a few parameters. Yeah. So 32 means that we're going to have 32 filters. The size of each filter is 3 by 3. Activation is ReLU. And we need to, for the first convolutional, we need to specify what is the input shape. And input shape is 21 by 21, or 28 by 28, 1. Why we need that? Because if we would have been dealing with the colored images, in that case, we would have been passing through 28, 28, 3. So that would have been our input, red, green, blue. Yeah. So afterwards, what we do the pooling layer with the 2 by 2 grid, and it's doing max pool, so it's just picking up the maximum. And afterwards, we do batch normalization, so to avoid this variance drift, and we do dropout. The half of the neurons which we are training now is going to be zeroed out. Now we do one more convolutional layer, now with 64 filters. Again, the filters are the same 3 by 3. Activation is again ReLU, and you're welcome to play with it. So you can change it to the tangent, to the sigmoid, and you can check those graphs which I had in the lectures, which are coming from some academic papers, so that if you take a ReLU, you have a quick training, but if you have, I don't know, tangent function as activation function, the training is much slower, and this is fully verifiable. Yeah. So again, we have a match pooling, batch normalization, sorry, and we have a dropout. And we have one more layer with the 64 filters, 3 by 3 ReLU. And now we just flatten it. So because we just flatten it because now we're going to pass it to the fully connected layer with 64 neurons and ReLU normalization. And the last layer which we need to add, we have a 10 classes, and activation is softmax again. Yeah. So okay, so this model now have a little bit more parameters. Yeah. No. In fact, no, not even more. No, much less parameters. Only 100,000 because here we have yeah, it's a 400,000 parameters, and here we have a 93,000 parameters, which is very good. All the rest is essentially the same. We compile in model, add them, categorical cross entropy, matrix accuracy, 10 epoch, batch size 128, a little bit smaller. And yes, let's train it and see. And you see it's visibly trained slower. Although it's a smaller number of parameters, but it's visibly trained smaller. And one of the reason is 128. We need to try to put back to 256. And that's why we're only doing 10 epochs. Otherwise, we've been sitting it here till forever. But the interesting thing is that because this is just a vanilla TensorFlow which I'm running on the CPUs. When you run it on the GPUs, you really see the difference. You really see that, yes, you understand why those graphical cards are that expensive, because these kind of problems, they accelerate not just drastically on the real data sets, on the larger ones. You don't need to have a special measurement to see the degree of acceleration. Yeah, but you see how the accuracy, validation accuracy growing, and we already overshoot our vanilla example from the DNN. Yeah. Now we're doing again model evaluate, getting history, training loss, validation loss, and you see how fast the training and test loss are dropping down. And yeah, they're still continuing, and one can continue. And the same with accuracy, how quickly accuracy jump up to the very high level on both and training on the validation set. And again, we can play the same game with the predictions. Yeah, so we can predict. So this is the image number 5 clearly, and we can check that the prediction is the same number 5. Yeah, or we can change the index to, I don't know. No, it looks like 8. And yes, in the predictions, it's really 8. What, by the way, this function is doing? NumPy argmax. So what does this line is doing? NumPy argmax prediction index. Any suggestions? So what is a prediction index? How it looks like? Let's prediction index. So prediction will be array of 10 numbers, 10 probabilities. Why? Because that is our last layer. Yeah. So our last layer is a dense layer with the 10 neurons, which we afterwards, where is my neural network? Activate using the softmax. So it's giving out 10 numbers. And after the softmax, these 10 numbers becomes probabilities. And now we need to find the highest probability out of all those. And it will correspond to the class. And we can now see what does it. So this is a very small number. Yeah. So let's do. So let's round it till 3 commas. And you see when in the moment when we round it, we see that there is only one number which is large enough. Yeah. So kind of if we let's so they're so small. Yeah, so we essentially almost don't see them. So the numbers for other probabilities are so small, so that essentially the one which correspond to the true index is so high. But in the other data sets, for example, if you get the pre-trained version of ImageNet or kind of or some VGG or AlexNet, and you do the predictions on the ImageNet data set, and you, for example, see that that the probability of the correct class could be like 70%, but afterwards it will be 20% for some other class. So it doesn't need, because here it's really the huge difference. Here it's obvious that it should be that it's a one class without options essentially. But with the larger problems and with the larger networks, it's not that clear, and you have some variability within the answers. Okay, and what is the argmax is doing? Any suggestions? Yeah, so getting the highest probability in the sparse vector output, but that's not the argmax is doing. Argmax, so we're getting, yes, we need to read out highest probability. That's absolutely correct. So, but what the NumPy argmax is doing, so it's getting the maximum, and where the 8 is coming from. Okay, so my internet is not that impressive right now. Okay. So it's essentially giving us the index of the corresponding entry. And because the index is corresponding to the actual number, because this will be 0, 1, 2, 3, 4, and so on, that is 8. That's why we're getting numpy argmax. Okay, so and very quickly, we can play absolutely the same game with some other. And there is also standard data set, which is called fmnist. And fmnist, F is standing for fashion mnist. So if you've never seen it, play with that because it's literally identical, but instead of digits, it have little images of the clothing items. But it's also 60,000 training data, 60 or 10,000 test data, and this is your typical examples of the items. So this is looking like a bag, and here is the several other items which you have in the data set. You play absolutely the same games as with digits, but with the items. And essentially here, we're doing the same, I think it's the same neural network. Yes, the same number of parameters. And just for the quickness, we can do 256. Yeah, it's a little bit better. Yes, getting the highest index value of that entry, yeah. And you see how quickly the accuracy is growing, because on the first run it's 17%, and afterwards it's 68, 85, 88, 88. So it's very quickly going to the quite a high value. And now it seems to be a little bit, yeah, but maybe the batch size is too large. Yeah, because it's a little bit getting stuck in the 88, which is okay, it's a good enough accuracy, but now you can also see how the batch size is affecting. Yes, but in principle, yes, the smaller batch size, the better. But the problem is that the smaller batch size, the longer you run. Yes, it's jumping to the 89. But still, yes, it's not 99 as we've seen just now with digits. But it's still good enough for the out-of-the-box prediction. Yeah, you see training loss, validation loss, both going down, but we can in principle keep training. Okay, and of course, we can do the predictions and we can do, again, play the same game, but the problem is that we need also now to find what is the class corresponds to. With the digits, we know exactly what class corresponds to, but for this one, we need to find some specifications in this data set. It should be so that it could tell us that there is what's class number 4 means, what class number 1 means, and so on. And I think that you can do it by yourself. Okay, I think we need to, do we have any questions? Because I think we need to slowly to wrap up. Otherwise, NITheCS leadership will be here and will kick me out. Could you please speak briefly on models that interpret model prediction? I'm not sure I understand the question. With that, which have interpretable model prediction, but it's all essentially models which you can write or draw on some final set of objects, like with a linear regression or other those logistic regression models and so on, or decision trees, where you can draw the diagram what's happening. Because the problem is with interpretability of the neural networks is this one, because what is a trained neural network model? Trained neural network model, it's this one, it's 100,000 numbers. And those numbers do not have a straightforward interpretation. You don't know what they mean. I mean, it's just the weights of the matrices, and kind of how to interpret them, it's not clear. But it works remarkably well. Yes, because it can solve a lot of pattern matching problems very nicely. But with those, as we have last time, okay, we don't, but just give me a sec. Like, I mean, that doesn't matter. When we were looking into these models yesterday, yeah, so we have that, oh, we can extract coefficients and rank coefficients in importance. And if you do it for some, so you can say, oh, this feature is the most important feature, and that feature is the most important feature, and you can check how much these, for example, first three features, how much of the variance in data they explain, and maybe using that, you can try to build a model which can predict for you things, but which will be already based, so you can think why, why it's 60% or 0.6 of the density, 53 or 0.53 of residual sugar, or and 0.2 of this type of acidity, and why it's working. And you can, with the domain knowledge from the field where you apply machine learning to, you can try to explain what you see. Do you understand what I mean? Because if you can produce a little formula which approximate the outputs, you can try to interpret this formula. You can understand why algorithm is thinking like that. But if I give you 100,000 numbers and say, oh, this is well-trained neural networks which can predict X, it will be very difficult to ask the question why and give a reasonable answer. And that is why it's rather difficult. Yeah, and I see that slowly the NITheCS leadership is coming in. Yeah. Okay, but notebooks are in the channel. You're welcome to use them. And you see, with the most of the notebooks, I also indicate where I took them from, so that yes, you can also try to see what are interesting things are around. Okay? I assume so, because there was a question, is now going to be the closing ceremony? Because Tutukili can guide us through. Tutukili, are you around? Okay, so I don't know about the access to Canvas, but I assume that one is going to have it for a little while.
Thank you for that, Prof. According to the schedule, I think by now we should be closing. I would like to open the platform for Prof. Francesco to give us his remarks.
Can we just wait just 5 minutes? We're not ready yet.
Who's that? Ah, so it's up. Do I have to stand there? Okay, because otherwise you don't see me here. Okay, so good afternoon. It's my pleasure to say some concluding remarks after the summer school. Yeah, I hope you all enjoyed it. Yeah, I had fun the day that, that I was with you. Yeah, so I hope you also had a little bit of fun doing that. I know that it's always very difficult to gauge the right level for this kind of schools. Yeah, because I picked up some of you mentioned that the entry-level test was way more difficult than the school afterwards. So that is something that we will take into consideration, and maybe for next year do better. Yeah? It is really important that now you probably today you will digest everything, yeah, but maybe next week you can give us some feedback, yeah, and tell us what you enjoyed, what you did not enjoy. Was the program okay? Was it too easy? Was it too difficult? Would you like something else? Yeah, there is a lot of need at all levels, because this week yeah.
A slide deck. What's that?
I don't know. I'm not showing any slide. Yeah. Yes. No, there is no slide on the screen. Yeah. Yeah. Anyway.
Okay, on this. Yeah.
Yeah. Okay. Anyway. Now I forgot what it was. Yes. No, there is need of training at every level. Yeah, because this month we started as NITheCS a mini school on really basic introduction to Python. Yeah, and there were 916 participants. Yeah. It's a lot, yeah, and we didn't advertise it particularly intensively, yeah, and I think what we will try to do is to build a kind of a series of short schools, yeah, to build up on that, yeah, and the other thing that I wanted to say is that you've been here now for 2 weeks, yeah. And with NITheCS, we organize every Friday, or at least we try to organize every Friday, what we call a micro school, yeah? Which is intended for a kind of peer-to-peer instruction. Yeah? Assume you have a particular skill. You know how to do nice slides in Beamer using LaTeX. Yeah? You can send us an email and offer a 20 minutes, half an hour maximum little course on the topic. Yeah? Just from student to student, yeah, and we have already a library of many of these micro schools from all possible topics, from plotting to solving some problem to implementing something to do something in LaTeX or in some other tools, yeah? And it's something that also attracts lots of viewers, yeah. And please stay engaged with us, and maybe next year one of you or two of you volunteer to act as tutor for the for the next round. Yeah, that would also be fantastic. Yeah, and in particular, those of you that are far away. Yeah. Everything is hybrid anyway, yeah. So please engage with us and stay in touch. Yeah. I don't know if now Benjamin wants to say a few words from the CHPC side. Benjamin, you're most welcome. Yes. Okay, Benjamin, can you hear us?
Yes, we can. Prof, can you hear me?
Okay, now we can hear. Yeah, please, if you want to say a few words, you're most welcome, now or never.
Yeah, sure. We're going to share a slide deck. So let me just get ready before we actually do the closing.
Hello, Benjamin. Maybe you can say a few words without sharing slides. But I think everybody's happy to go into the weekend now.
Sorry, Prof, we have some prizes to give away, so hence the slideshow.
Okay. We don't see the slides.
Yes, they are coming.
Okay, very good.
We did get out more. Being prizes for that. I'll see you now. The device jump on the bike and play golf. Doesn't make sense.
Francesco, can I say a couple of words and I'll stop immediately when it's
You're welcome, because this
just covering you. My name is Lawrence, and I'm from Germany, and I will shut up.
we can see the slides.
There's an advance.
Jerusalema ikhaya lami ilondoloze uhambe nami zungangishilana Jerusalema ikhaya lami ilondoloze uhambe nami zungangishilana dawo yami ayikholana buso wami awukholana ilondoloze zuhambe nami dawo yami ayikholana buso wami awukholana ilondoloze dawo yami ayikholana buso wami awukholana ilondoloze zuhambe nami dawo yami ayikholana buso wami awukholana ilondoloze Jerusalema ikhaya lami ilondoloze uhambe nami zungangishilana Jerusalema ikhaya lami.
All right, thank you, everyone. Hopefully everybody was inspired and ready to finish the coding summer school for today. For the last time, I'm going to, hopefully everybody can hear me. I'm going to ask in our favorite channel, is everybody ready? The last time, can I give my thumbs up in the Slack channel? Is everybody ready for the last time? Hopefully we have learned our lesson and I want to get extra thumbs. Please give me thumbs up to know we are ready for the final session and closing session for today.
This thumbs down. Others still not getting thumbs.
All right, let's begin. So this is the final session for today. We had long 2 weeks. Let's get into it. Hopefully it won't take too long. Again, the Coding Summer School was a huge event that was started many months ago with many people involved, many teams involved to make this happen, to make this all work. Champions have been involved from the beginning to make this work. The tutors and admin staff to make sure there's a venue, there's food, there's snacks, there is internet and projectors and seating for all of you. So a huge thanks to all of them. It couldn't have been done without all of their help. In terms of the agenda today, hopefully it's going to be short and sweet. We're going to have a quick look at what the Coding Summer School was all about and hopefully some objectives we try to achieve and hope you learn something. Some highlights from the past 2 weeks. The most important thing is prizes. We're going to speak a little bit about the post-coding summer school, what's going to happen, and then importantly, certificates. So my little insight that Prof. Ilya showed us yesterday was from his slide. And this, I think, summed up a combination of the coding summer school, where we have the data, which we've been working with for the past week, cleaning data, loading it. We did ETL, EDA. We did many things to understand and prepare the data before we even get to machine learning. And Monday, we had Prof. and Deepika explain to you algorithms, how to develop and write algorithms. And all of this culminated in these last 2 days in machine learning to give you a very good, very solid foundation and a good overview of machine learning. So hopefully, you've learned something, and hopefully this will not be the last time you learn, about these skills. So again, the team from the CHPC is a big group of us that led this to make sure it works for the past 6 months and even longer. In the next few weeks, we're going to start preparing for the 2027 and learning and from what happened here and moving forward. I'm not sure if Krishna is, yes, Krishna is there. Krishna, do you want to say a few words as well?
Okay, yeah, because I know it's Friday afternoon. Everybody is ready to go home now, right? So, just quickly from my side, thank you all for joining, firstly. So, I think we give yourselves a round of applause for making it through the 2 weeks. So, from our side, both CHPC, thank you guys also for all of the hard work that you guys have done. And from the NITheCS team as well, well done to everyone. And specifically the champions, because guys, you don't get enough credit. I'm a champion on my end as well. It's a lot of work to organize venues, get everything sorted. So thank you to the champions and thank you to everyone and students mainly. Thank you very much. And just on a note, remember I warned y'all before you start. This is going to be an intense 2 weeks. I wasn't lying, right? It's data overload. So it is information overload. We know there's a lot of stuff that you'll learn, lots of topics being covered, but it's up to you all to not take it further. So if you want to expand on certain things, please make sure you go and expand on them and learn about these things and apply it to your own research. That's the only way you're going to learn, right? And then finally, just to make sure that in all of your cases, remember, as Prof. Francisco has highlighted, NITheCS has events monthly. And these NITheCS events will also assist you in learning some of these techniques. So make sure you subscribe to the YouTube channel and attend these events when they are available. They usually send out the letters to everyone. So if you're a NITheCS associate or NITheCS member, you will get these letters. Attend these events because they are very beneficial. So that's it from me. Thank you very much, guys. And thank you for attending.
Prof, do you have any extra words?
Sorry, Benjamin. I think I just said a few words at the very beginning, so please go on.
Okay. All right, so some highlights I picked up and got from a few other people. Week 1, how to get movies from torrent. How to respond with thumbs up and emoticons. Where has Streamlit been all my life? We learned what's research software engineering, and we are pretty much all research software engineers. We did a very fun team building exercise. We learned how to start a bike rental business if you are in South Korea. We learned the challenges of installing different libraries. And we learned that conda env is our friend. We used bash to fight monsters, and we drew colorful plots of South Africa. Week 2, we learned about algorithms and how Google Colab just gives you the answers. And we did an intro to stats and learned new features with Spider. We had a stand-up comic, give us gruesome lessons on probability and statistics. And everything we learned so far culminated in machine learning lessons. We had a good AI research guidelines, and we learned how to predict housing data and much, much more. So the prize is why we're all here and waiting late on a Friday afternoon. We have 7 prizes to hand out, 3 Pythonista awards, 2 Streamlit awards, and 2 Slacker awards. So each of these recipients get a 500 Rand gift voucher from Exclusive Books. So the Pythonista Award, these are for students that has excelled with in terms of the quizzes and the Streamlit app. They were just literally the top 3 best students that completed all the quizzes on time and performed the Streamlit app assignment, very well. So let's see who these people are. So, drum roll, please. So, Seski Nguza from Univen, Grace van Heerden from UCT, Felasande Shusha from CPUT. Well done to these students. You are the top Pythonistas for the Coding Summer School 2026. And well done to you. You will be receiving an email from NITheCS on how to receive your award and hopefully use it for something useful. So I'll put these names on Canvas and Slack as well, so everybody can congratulate them as well. So the next awards is the notable Streamlit apps. So Streamlit, as you know, as everybody can imagine, was very popular, and we got a whole range of people doing different kinds of apps, just sharing them, and it was pretty cool to see. So the first set are just notable Streamlit apps. People did fun things with them, and then we'll get to the more the apps that were more the research profiler app, which were focused on actual awards. So just some fun ones people did create is a Valentine's partner app. Fill in your name and CV if you want a Valentine. We had one last year as well. This one asked for CV as well, which is quite interesting. So again, you can check out these on the Slack, on the Streamlit channel. This was quite interesting as well. Somebody created a 3D PDB viewer. So this is obviously an image of it, but it can rotate and whatnot. So this is a 3D PDB viewer. Somebody created a glow guide beauty powered by Crafty. So you can input your type of skin and your budget, and you get recommendations for the type of makeup or whatnot you can buy for your type of skin. Somebody created a game, tic-tac-toe game. I did play it and it was quite well done, so that was pretty interesting. Somebody created a student life balance tracker using different widgets to showcase what they can do with Streamlit and having fun with it. Somebody created a page to transcribe African melodies. So I had quite interesting to have a look at this. So if you're interested, check out Streamlit, or you can have a look at what they've shown there. All right, so this is more specifically the what the awards were focused on, the researcher profile apps. And again, this was quite difficult to score. There were hundreds of submissions. We had to drop that down to 75, I think, or 72. And of the 72, we had to drop that down to 10. And of those 10, we had to choose 2. So it's quite an intense process, to find, the best apps that students created. I'll show you the top few that were the top few that were selected in the top 10, just to give you some guidelines. So the one which is pretty good was Jess. Where's Jess? Pretty good app that she created, quite a lot of detail which we were looking for. Had a nice feature with the image where you can change between 2 images to find the X-shape galaxy. We had Kavir, so quite a lot of detail. Kavir went into developing the researcher profile, a lot of pages and different content that was added to the site. So this was also very well done. This is probably the nicest looking site by Charlene Cockcroft. A lot of effort went into it, making it look really nice. And it was a very cool game that she added on one of her pages. I think probably a widget that was added from another site, but it was quite a cool site that she added and she created. Then we have Veneretta. So she also created a very good website, a lot of content that was added, quite in-depth and quite impressive. And then with Arno as well, Arno had also very nice visually well-presented website, Streamlit app. Went into quite a bit of detail as well with presenting his content. All right, so the Streamlit Awards for 2026 goes to Veneretta Mdaka from UMP and Agisa Kavir from UP. Well done. Well done to both of you. Again, we'll put your names for the Streamlit Awards on Canvas as well as Slack. So on Slack, you can also ask them for the for the site, so you can have a look at it as well. So well done again to all of them. All right, the Slack Awards. So Slack, we've become very familiar with Slack. It's become our friend and enemy. We've learned how to give thumbs up appropriately and give different types of emoticons. But there are 2 awards for Slack, and that we looked at students that were most active on Slack and students that were most helpful on Slack as well, helping the colleagues and giving proactive content or responses in Slack. So we have 2 awards again for Slacker Awards. So drum roll, please, for these 2 students. And it goes to Tendo Ravele from Univen with 132 posts, and Arno Smith from Northwest University from Potchefstroom, 70 posts. So well done to both of them. They, again, will be getting the email from NITheCS and letting them know about the award for the book voucher. So well done to all of you for those that have won. All right. What happens after the Coding Summer School? Well, Slack and Canvas will still be active for now. We will be posting, CHPC and NITheCS will post some upcoming events. There is some feedback. There's a feedback form for week 2, which will be posted shortly after this closing session. Please complete that. Week 1 has been well, responded to. So please also week 2, week 2. After coding summer school, please continue your Python journey. So please join Python communities. There are very strong and active ones in South Africa itself. Join PyCon ZA. It is a PyCon ZA conference that's happened. So people from across the country join and showcase what they're doing in various Python fields. So it was last year in Joburg, and this year it's going to be in Cape Town. So in October 2026, around that time. So please join that. It's very beneficial to just see what other Pythoniers and Pythonistas are doing. Again, continue your journey. There are many sites and online sites. I'd recommend DataCamp is one of them. If you are keen on data science and machine learning, it is a paid site, but I definitely recommend DataCamp. We will post more events from CHPC for the winter school. That happens August, and our national conference, which is end of this year. And the NITheCS has many schools and colloquiums. They will be posting their events, and there's much, much more. Check out their sites, CHPC site and the NITheCS site as well. And then lastly, your certificates. So on Monday, an announcement will be made on Slack to check the certificates channel. So there's a channel that will be that is created already. So check that channel. You'll be given a link to go to download your certificate. Input your surname if it is there, if you met the criteria, follow the instructions to get your certificate. And that is it. Thank you so much.
Thank you, and thank you to you, Benjamin.
Thank you, Benjamin and Tutukila. I think that's it. Yeah. So thank you very much again, everyone. And maybe we see some of you next year in another role. Yeah, in the role of tutors. Yeah. So thank you very much. I think that's it for this year. Thank you.